R136A1 is the most massive star currently known to science, a cosmic leviathan whose very existence challenges the limits of astrophysics. It belongs to a special, elite class of stars that aren't just big, but impossibly big. First identified as part of a dense stellar cluster within the Tarantula Nebula, R136A1 immediately stood out due to its sheer brightness and energetic profile. When scientists studied the light coming from that region, they discovered that this one star, among many in the cluster, was emitting more energy than millions of suns combined. Upon deeper investigation, R136A1 was revealed to be something unprecedented in the known universe. But before we continue, subscribe to the channel so you don't miss out on any of these videos. The name, R136A1, isn't arbitrary. It points to its home in the R136 cluster, which itself is part of the larger star-forming region known as Derise, located in the Tarantula Nebula. The A1 designation indicates that it is a distinct, individual component of the R136 cluster. But make no mistake, this is not a typical star among peers. R136A1 is in a league of its own. From our Earth-bound perspective, it's invisible to the naked eye despite being one of the brightest stars known. Its immense distance of about 160,000 light-years away makes it invisible without the aid of powerful telescopes. Yet, even from that unimaginable distance, the light it emits has been observed and measured by some of the most advanced instruments in astronomy. Basic statistics of this stellar behemoth are staggering. At birth, R136A1 is believed to have had a mass of approximately 315 solar masses. That means that it was over 300 times the mass of our own Sun, something many theoretical models suggest shouldn't even be possible. Today, due to intense stellar winds and mass loss, it's estimated to be closer to 200 to 215 solar masses. Still, that's enough to dwarf any other known star in the universe. It's not just mass that sets it apart. Its luminosity, how bright it shines, is estimated to be somewhere between 8 and 10 million times that of the Sun. If R136A1 were placed at the center of our solar system, it would utterly obliterate everything we know. Earth wouldn't just be scorched, it would be consumed. In fact, the entire planetary system would likely be unstable in the presence of such overwhelming radiation and gravity. But what is it fundamentally? R136A1 is classified as a wolf-rayet star, a type of evolved, high-mass star that burns through nuclear fuel at an astonishing rate. These stars are incredibly hot, bright, and unstable. They're known for their powerful stellar winds, streams of ionized particles blown into space by intense radiation pressure. R136A1 fits this description and more, pushing every known boundary of what such stars can be. Its existence alone forces astrophysicists to rethink what is possible in stellar evolution and formation. How can something this massive form in the first place without tearing itself apart during the process? How does it stay stable? And perhaps most importantly, how long can it last? R136A1 isn't just a superlative among stars, it is an outlier that defies the rules, a monument to the extremes of stellar physics. It's a singular case study that provides both a warning and a wonder. The cosmos is far more powerful, far more mysterious, and far more magnificent than we often imagine. Hovering far beyond the reach of our unaided vision, R136A1 resides in one of the most turbulent and extraordinary neighborhoods in our galactic vicinity, the Tarantula Nebula. This vast and chaotic stellar nursery, officially known as Derise, lies nestled within the large Magellanic Cloud, a dwarf galaxy that orbits the Milky Way at a distance of roughly 160,000 light-years from Earth. It's a place of violent birth and energetic youth, where cosmic conditions are so extreme that they can give rise to some of the most massive and luminous stars in existence. The Tarantula Nebula isn't like the serene star fields we often imagine in our night skies. It's a roiling cauldron of radiation, plasma, and interstellar gas, glowing in hues of electric blue and crimson pink due to intense ultraviolet light streaming from newborn stars. It stretches across hundreds of light-years and contains some of the highest concentrations of massive stars ever observed. In the middle of this fiery chaos lies the R136 star cluster, and at the very heart of that cluster is our 136A1. To understand the significance of its location, consider the environment of 30 Doradus. It is the most active star-forming region in the local group of galaxies, the set of about 50 galaxies that includes the Milky Way. The conditions here are similar to those that existed in the early universe, making it an incredibly valuable natural laboratory for astronomers studying how the first stars may have formed. And within this cosmic furnace, the R136 cluster stands out as a gravitationally bound collection of the most massive young stars known, many of them exceeding 100 solar masses. R136A1 is not merely a product of this environment, it is the apex of it. It represents the upper limit of what such extreme cosmic conditions can produce. Its location in the core of this energetic cluster is not a coincidence. The density of matter, the high-energy radiation, the turbulent gravitational interactions, all of these ingredients have created the perfect storm for a star like R136A1 to be born and sustained, at least for a brief period in astronomical terms. The Large Magellanic Cloud itself provides an interesting context. Unlike the spiral structure of our Milky Way, the LMC is irregular, its star-forming regions not evenly distributed but instead clustered in pockets of activity like 30 Doradus. Its relative proximity allows astronomers to study these processes in greater detail than we could in more distant galaxies. The Tarantula Nebula is the brightest emission nebula in any galaxy visible from Earth, and is so luminous that if it were only as far away as the Orion Nebula, just over 1,300 light-years, it would cast visible shadows at night. And our 136A1 is the jewel at the center of it all. Its intense radiation contributes significantly to the overall luminosity of the nebula. Its stellar winds shape the surrounding gas clouds, carving out structures, compressing matter, and possibly even triggering new rounds of star formation. It is not just a passive resident in its galactic home, it is an active architect of its environment, influencing the region on both small and large scales. In this extraordinary setting, far removed from the quiet suburbs of our own solar system, our 136A1 lives its short, brilliant life in the most dramatic of cosmic theaters. The Tarantula Nebula and the Large Magellanic Cloud are not just backdrops, they are integral to the story, providing the physical conditions, materials, and forces necessary for a star this massive to even be possible. Without such an environment, a star like our 136A1 might never exist at all. The story of our 136A1's discovery begins not with a single eureka moment, but as a gradual unveiling, an unfolding cosmic mystery revealed through decades of technological advancement and increasingly sophisticated observation. For much of modern astronomy's early development, even the existence of such ultra-massive stars was speculative at best. Stars as luminous as our 136A1 were once believed to be either impossible or simply too unstable to survive long enough to be observed. Theoretical limits on stellar mass suggested a maximum of around 100 to 150 times the mass of the Sun. Anything beyond that was expected to be too unstable, fragment during formation, or collapse under its own gravity before it could shine. And yet, hidden in the southern skies, deep in the heart of the Tarantula Nebula, something far more massive had already been burning for hundreds of thousands of years. Astronomers had long known that the Tarantula Nebula was special. Even with modest telescopes, it glowed with an intensity unmatched by any other nebula in the local group. Early observations in the 20th century revealed it as a hotbed of star formation, a region so active and bright that it demanded deeper inspection. However, the true nature of the R136 cluster, and in particular R136A1, remained obscured by distance and the limitations of available technology. The cluster appeared as a single point of light or, at best, a blurry object that seemed like one star but behaved as though it were many. The first serious clues came with improvements in ground-based telescopes and photographic plates in the 1970s and 1980s. When astronomers began using higher-resolution spectroscopy and photometry to analyze the light coming from our 136, they noticed something unusual. The energy output was far too great for a single star. Some believed it must be a massive cluster of tightly packed stars, possibly hundreds of them, all shining together, and giving the illusion of a single superluminous object. This idea persisted for a time. It was the most sensible explanation, given the existing models and observational constraints. But as observational astronomy leaped forward in the 1990s and 2000s with the launch of the Hubble Space Telescope, clarity began to emerge. Hubble's sharp optics provided unprecedented views into the dense R136 cluster. What had once seemed like a single point of light could now be resolved into individual stars. Among them, R136A1 stood out as the brightest and most massive. Even within a field of giants, it shone orders of magnitude more intensely. Using both imaging and spectral analysis, astronomers were able to isolate the characteristics of R136A1, its unique spectrum, its brightness, and its estimated mass. The key breakthrough came when they could determine the star's luminosity and temperature, which together allowed for estimates of its mass based on stellar models. This wasn't a trivial calculation. At such extreme energies, even small measurement errors could result in large variations in mass estimations. Nevertheless, the numbers kept coming back with the same shocking result. This star was more massive than any other previously recorded, potentially over 300 solar masses at birth. The pivotal paper that announced R136A1 as the most massive star known was published in 2010 by a team led by Paul Crowther at the University of Sheffield. Using observations from the European Southern Observatory's Very Large Telescope, VLT, in Chile and archival Hubble data, they combined high-resolution spectroscopy with stellar atmosphere modeling. The team estimated the current mass of R136A1 to be around 265 solar masses, with its initial mass at formation likely closer to 320 to 325 solar masses. These numbers shattered previous theoretical limits and forced astronomers to re-examine the upper boundaries of stellar mass formation. This wasn't just a discovery of record-breaking proportions, it was a discovery that forced an evolution of thought. The implications of R136A1's existence extended far beyond the Tarantula Nebula. If one such star could form, what did that mean for the early universe, when stars were generally more massive and conditions more extreme? Could even larger stars have once existed, possibly going unobserved because they lived short, explosive lives in the ancient cosmos? Moreover, R136A1 wasn't alone. The R136 cluster contained multiple stars exceeding 100 solar masses. While none approached the size of R136A1, their collective presence suggested that the region had somehow enabled a rare stellar phenomenon, the formation and sustenance of ultramassive stars. This added to the mystery. Why here? What was different about this region that made such cosmic giants possible? The discovery of R136A1 also illuminated just how dependent modern astronomy is on technological advancement. Without the resolving power of space-based telescopes like Hubble and ground-based facilities like the VLT, R136A1 might have remained indistinguishable from its neighboring stars. Even today, distinguishing such stars requires sophisticated instruments capable of cutting through dense interstellar gas, correcting for atmospheric distortion, and interpreting complex spectral data. The star's detection was not simply the result of pointing a telescope and taking a picture, it was the culmination of decades of accumulated knowledge, computing power, and observational skill. And the discovery continues to evolve. As newer, more advanced telescopes come online, like the James Webb Space Telescope and the upcoming Extremely Large Telescope, ELT, astronomers hope to gather even more detailed information about R136A1 and its surroundings. Future observations will aim to refine estimates of its mass, understand its rotation rate, map its stellar winds, and monitor its evolution in real time. Each new data point is a clue in the unfolding story of one of the universe's most extreme objects. But perhaps what makes the discovery of R136A1 truly profound is not just the science, it's the reminder that even in our era of high-tech exploration and well-mapped skies, the cosmos still holds secrets that defy logic and expectation. For years, astronomers looked into the heart of the Tarantula Nebula and saw only a blur. Today, we know that hidden in that blur was a star so massive it rewrites the textbooks. Its discovery serves as a symbol of cosmic humility, a signal that the universe is deeper, stranger, and more powerful than we ever dared to imagine. At the heart of the Tarantula Nebula lies one of the most extreme stellar environments in the known universe, a densely packed cluster of massive stars known as our 136. This is the birthplace and current home of our 136A1, and understanding the nature of this incredible cluster is essential to grasping how such a monster star could even form in the first place. Our 136 is not an ordinary cluster by any measure. It's a cosmic crucible where nature forges giants, and its properties defy many of the traditional expectations astronomers hold about star formation, density, and gravitational interaction. The R136 cluster is the central core of a much larger stellar grouping known as NGC 2070, which itself lies within the 30 radius region. What sets R136 apart is its remarkable concentration of extremely massive, young stars in a relatively small volume of space. This is not a gentle gathering of suns spread thinly across the void. This is a stellar city on fire. In fact, the density of our 136 is so great that if you were to replace our Sun with this cluster in the center of our solar system, the sky would be lit by thousands of visible stars, many of them brighter than a full moon. Composed of mostly population 1 stars, those rich in metals and born in recent epochs, our 136 is thought to be less than 2 million years old. In astronomical terms, that's an eye blink. Its youth means it's still radiating the intense heat and ultraviolet light typical of newly formed stars, and these emissions bathe the entire Tarantula Nebula in a glow of high-energy radiation. The sheer brightness of the region is largely due to the collective luminosity of our 136's members, many of which individually outshine whole galaxies when measured across all wavelengths. Within this maelstrom are stars with masses ranging from tens to over 100 times that of the Sun. It's not just our 136A1 that's massive, there's our 136A2, our 136A3, and several others, all with exceptional masses. While our 136A1 leads the pack, several other stars in the cluster are believed to exceed 100 solar masses, making this region the largest known concentration of very massive stars. This dense population offers astronomers an unprecedented opportunity to study stellar evolution at the high-mass end of the spectrum, something that's exceedingly rare in the cosmos. One reason these massive stars are clustered together so tightly has to do with the nature of the molecular cloud they formed from. Massive stars tend to form in clusters because the same high-density conditions that allow a large amount of gas to collapse into one giant star often give rise to many more stars nearby. But our 136 takes this to an extreme. It may be the closest analog we have to the superstar clusters believed to exist in starburst galaxies or in the early universe, compact groups of extremely massive stars that formed when the cosmos was young and turbulent. Yet such tight packing of powerful stars isn't without consequence. These giants interact gravitationally, and sometimes violently. Stellar winds from each star collide with those of its neighbors, creating shock fronts and turbulent gas flows. These winds can also strip away material from surrounding protostars, influencing their growth and potentially preventing smaller stars from ever forming. Radiation pressure from stars like our 136A1 can shape the interstellar medium itself, carving out cavities in the nebula or even triggering the collapse of nearby gas pockets, leading to new waves of star formation. The energy dynamics within our 136 are intense. UV radiation from its stars ionizes hydrogen gas in the surrounding nebula, creating regions that glow vividly in optical wavelengths. X-rays and gamma rays are also emitted, making the cluster an active target for multi-wavelength observatories. This intense feedback is not only transforming the surrounding environment, it's also regulating the life cycles of the stars themselves. Mass loss to radiation and winds is accelerated in such crowded, high-energy environments. Our 136A1, for example, is shedding mass at a dramatic rate, a process driven in part by the intense conditions around it. One of the most fascinating aspects of our 136 is that despite its density, it seems to be gravitationally bound. That is, the stars within the cluster are not flying apart despite their powerful gravitational forces and fast motions. This suggests a strong central mass concentration and a high total cluster mass, perhaps exceeding several 100,000 solar masses when accounting for both visible and unseen members. However, there's still much debate about whether our 136 will remain stable long-term. Over millions of years, gravitational interactions could eject some stars from the cluster or even cause it to dissolve entirely, dispersing its massive members across the large Magellanic Cloud. For now, our 136 remains a stellar pressure cooker, where the extremes of mass, heat, and luminosity converge. It serves as a real-time laboratory for testing theories of star formation, especially under conditions that may resemble those from the early universe. In many ways, studying our 136 is like peering into the past, into the ancient days of cosmic evolution when the first stars blazed into life in primordial hydrogen clouds. And yet, for all its value, the cluster still holds mysteries. The precise mechanisms that allowed so many massive stars to form in such proximity remain the subject of intense research. Why haven't more of these stars collided? Could our 136 be hiding even larger stars that we simply can't resolve yet? Are there intermediate mass black holes forming from unseen supernovae in the cluster's dense core? These are just a few of the questions scientists are exploring using data from telescopes like Hubble, Chandra, and in the near future, the James Webb Space Telescope and the Extremely Large Telescope. Ultimately, the existence of our 136A1 can't be separated from the cluster it resides in. Without our 136's uniquely violent and fertile environment, a star of such incredible mass might never have existed. Our 136 is not just the setting for the story of our 136A1, it is the cradle, the furnace, and perhaps eventually, the graveyard of giants. To study the cluster is to witness the universe at its most ferocious, where the birth of stars is not a quiet glow in the dark but a cosmic eruption of unimaginable scale. When we talk about the size of our 136A1 compared to our Sun, we are entering a realm so extreme that it defies ordinary comprehension. The numbers don't just represent incremental differences, they illustrate an entirely different scale of stellar existence. The Sun, the powerhouse that sustains life on Earth, becomes almost diminutive when held against this colossal giant of the Tarantula Nebula. Our 136A1 isn't just a bigger star. It is a different category of object altogether, something so massive, so luminous, and so ferocious that it bends the very boundaries of what a star can be. Let's begin with mass, the most staggering aspect of our 136A1. Estimates suggest that our 136A1 currently has a mass of around 265 times that of our Sun. But more astonishingly, when it first formed, it may have been as massive as 320 to 325 solar masses. This is not just an anomaly, it's a direct challenge to the long-held assumption that the theoretical limit for stellar mass formation was around 150 solar masses. Our 136A1 has more than doubled that. In a single star. To put this into perspective, if the Sun were a standard sedan, our 136A1 would be a kilometer-long freight train of nuclear fire. Its immense gravity alone is enough to bind vast regions of gas, yet paradoxically, it's also constantly fighting against its own mass through the incredible force of radiation pressure, a battle that defines its internal structure and lifespan. Now consider its radius. While the Sun has a radius of about 696,000 kilometers, our 136A1 is estimated to be 30 to 35 times larger in radius. That might seem relatively modest compared to red giants, but it's important to remember that our 136A1 is not a bloated, cool star. It's a compact, high-temperature, high-mass wolf-rayet star, meaning it crams all of its mass into a much denser and hotter volume than most other stars. Despite its relatively smaller physical size compared to red supergiants, its core is packed with nuclear fury. If you were to place a 136A1 where the Sun is in our solar system, it would stretch to engulf the orbit of Mercury, maybe even more. But unlike a red giant, it would emit blistering ultraviolet radiation that would roast all the inner planets to ash within seconds. That brings us to energy output, a domain where a 136A1 leaves everything else in the dust. The Sun produces about 3.8 times 10 superscript 2 watts of energy every second. That's an enormous number, more than enough to keep Earth alive and warm over billions of years. But our 136A1? It emits over 8.7 million times more energy than the Sun. Not 10 times. Not 1,000 times. Millions. This gives it a bolometric luminosity, total power output across all wavelengths, that exceeds 10 solar luminosities. This means that in a single second, our 136A1 radiates as much energy as the Sun would in nearly 3 months. And this energy is not primarily visible light, like the Sun's warm yellow glow. Instead, our 136A1's output is dominated by extreme ultraviolet radiation, X-rays, and even gamma rays, bathing its environment in radiation that ionizes gases, strips electrons, and warps the surrounding nebula with photonic pressure. These energy levels are so immense that they literally push matter away from the star's surface in the form of powerful stellar winds, shedding several Earth masses of material per year in the process. Moreover, this energy is tightly coupled with surface temperature, which we'll dive into more deeply later. But suffice it to say for now that our 136A1's photosphere burns at over 53,000 Kelvin, nearly 10 times hotter than the Sun's surface temperature of approximately 5,800 K. The hotter the star, the more energy per second it emits from each square meter of surface area, according to the Stefan-Boltzmann law. So not only is it larger, but every inch of it is radiating magnitudes more power than the same area on the Sun. All of this energy translates into intense gravitational and radiative forces, which influence everything from nearby stars in the cluster to the very gas and dust of the Tarantula Nebula itself. Our 136A1 is not just a source of light, it's a cosmic engine, actively reshaping its surroundings through raw output. And yet, all this power comes at a price. Because of its overwhelming mass and furious energy consumption, our 136A1 burns through its nuclear fuel at a breakneck pace. The Sun, with its calm and measured fusion rate, can expect to shine for about 10 billion years. Our 136A1, on the other hand, is likely to live for only 2 to 3 million years, a brief, violent flicker in the galactic night. It's the stellar equivalent of a supernova in slow motion, brilliant, short-lived, and destined for a spectacular end. The differences in scale between our 136A1 and the Sun aren't just quantitative, they're qualitative. The Sun represents stability, moderation, and longevity. Our 136A1 is about extremes, extreme mass, extreme radiation, extreme temperature, and an extremely short life. If the Sun is the comfortable campfire of the cosmos, our 136A1 is the detonation of a nuclear warhead, brilliant, unrelenting, and unsustainable. And that size, power, and destructive elegance lie at the heart of why this star continues to fascinate scientists. It's not just big, it's rewriting the laws of what we believed stars could be. It reveals that under the right conditions, nature can bypass our models, shatter our limits, and produce something that exists not on the edge of possibility, but beyond it. Our 136A1 is, in many ways, a cosmic contradiction. It exists, it burns, and it dominates its environment with extraordinary force. But according to our long-standing models of stellar physics, a star like this should be impossible, or at least so improbable that finding one ought to be akin to discovering a black swan in a world that believed only white ones existed. And yet here it is. Our 136A1 doesn't just stretch the limits of what we thought stars could be, it outright breaks the rules, confronting scientists with a puzzle that has sparked re-examinations of how stars form, how they survive, and where the upper limit of mass truly lies. For decades, astrophysicists believed that the maximum mass a star could attain through natural formation processes was around 150 solar masses. This limit was based on a balance of forces, mainly between gravity pulling matter inward and radiation pressure pushing outward. As stars grow in mass, the radiation pressure from their core fusion becomes more intense. At a certain point, this pressure is so powerful that it should prevent further accretion of gas, essentially placing a cap on how massive a star can grow. This concept was backed by numerous computer simulations and theoretical frameworks. It was a comfortable ceiling. But a 136A1 blows that ceiling wide open. When first observed and studied, our 136A1 shattered expectations by weighing in at over 265 solar masses, with some estimates suggesting it may have originally been more than 320 solar masses at birth. That's more than twice the accepted upper limit. It's not a small margin of error, it's a radical deviation. This discovery forced astrophysicists to go back to their models and ask, how can this be? If our 136A1 formed naturally within its cluster, then clearly the rules aren't what we thought they were. One possibility is that our understanding of accretion limits, the process by which stars gather mass during their formation, has been incomplete. Normally, as a protostar becomes more massive, it emits intense radiation that pushes back against the incoming gas. The idea is that eventually, the outward pressure becomes so strong that it halts further accretion. But what if under certain extreme conditions, such as those found in dense stellar nurseries like our 136, the gas is funneled in faster than the radiation can repel it? Or what if magnetic fields and disk-like accretion structures allow the gas to bypass the intense radiation field and continue falling onto the star from less hostile directions? There's also the possibility of stellar mergers. Some researchers propose that massive stars and dense clusters can form through the collision and fusion of smaller stars. In an environment like our 136, where stars are packed closely together, gravitational interactions can cause binary systems to tighten or destabilize, eventually leading two stars to spiral into one another. The result is a supermassive star that defies traditional formation models. Perhaps our 136A1 wasn't born in one piece, but rather built itself through cannibalism. It could be a Frankensteinian product of cosmic violence. Another angle scientists are exploring involves metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium in a star-forming region. Lower metallicity environments tend to produce more massive stars because metals in the gas cloud can contribute to opacity, which enhances radiation pressure and can limit mass growth. The Large Magellanic Cloud, where a 136A1 resides, has a lower metallicity than the Milky Way, potentially allowing for the formation of larger stars. If the star-forming environment is less resistant to gravity and radiative feedback, then stars might grow bigger before hitting that theoretical wall. But none of these explanations fully settle the matter. Our 136A1 stands as a massive outlier, one that still baffles even the most advanced models. Its existence calls into question whether our estimates of upperstellar mass are too simplistic. Perhaps there's no single, universal cap, but rather a range that depends on local conditions like gas density, magnetic field strength, cluster dynamics, and metallicity. In this light, our 136A1 becomes not just a monster star, it becomes a test case for the very limits of astrophysics. And beyond formation, there's also the matter of stability. Even if a star like our 136A1 can form, how can it remain stable without blowing itself apart? Stars of such enormous mass generate an incredible amount of internal pressure, and as they fuse hydrogen into helium and then into heavier elements, the energy output becomes extreme. So why hasn't our 136A1 torn itself asunder? The answer may lie in its internal structure. Supermassive stars like this are likely to have a very different internal gradient, where the core and outer layers operate under different fusion regimes. Some models suggest that internal mixing processes, like convective overshoot or rotational mixing, might allow them to burn more efficiently and delay instability, at least temporarily. Still, it's a ticking clock. Stars this massive burn fast and live short. But before it dies, our 136A1 is offering us a front-row seat to the high-energy physics of the universe's most extreme objects. It's forcing theorists to reconsider star formation at cosmic dawn, when metallicities were lower and densities higher, conditions under which the first, so-called population 3 stars might have been even more massive than our 136A1. In that sense, this star isn't just unusual, it may be a bridge to the early universe, a glimpse into the kinds of stars that lit up the cosmos for the first time. And that makes its challenge to our models even more urgent. If we can't explain how our 136A1 came to be, how can we accurately model the first billion years of stellar history? How do we know what kinds of black holes the early universe seeded? How do we trace the origins of the elements that now make up everything we see? Our 136A1 may just be one star in a distant cluster, but it's rewriting textbooks. It stands as a defiant cosmic statement that nature does not always obey the rules we set for it. Sometimes, the universe doesn't just whisper its secrets, it shouts them. And sometimes, those secrets take the form of a star too big to believe. In the grand theater of the cosmos, stars live on vastly different timelines. Our sun, serene and middle-aged, is a long-burning hearth that provides stable energy for billions of years. But our 136A1 is no such calm and steady beacon. It is a stellar inferno, a furious burst of cosmic energy that burns so brightly and so violently that its lifetime is more of a dramatic flash than a slow simmer. When we talk about the life expectancy of our 136A1, we are forced to abandon any notion of longevity. This is a star that, by cosmic standards, was born to die young. While the Sun is expected to live for about 10 billion years, our 136A1's projected lifespan is staggeringly short, only about 2 to 3 million years. It's already well into that life, possibly halfway through or more. That means, in all likelihood, our 136A1 has been shining for less time than it took humanity to evolve from early primates. And yet, in that short span, it has expelled more light, radiation, and matter than our Sun will over its entire 10 billion year existence. Why such a short life? The answer lies in the relationship between a star's mass and its rate of fuel consumption. High-mass stars like our 136A1 burn through their nuclear fuel at astonishing rates. Despite having hundreds of times more mass than the Sun, our 136A1's luminosity, its energy output, is millions of times greater. That means its internal fusion engine is running hot, fast, and at nearly maximum throttle. It's the equivalent of revving a sports car engine at full speed from the moment it rolls off the assembly line. The ride is spectacular, but it ends quickly. Fusion in stars begins with the conversion of hydrogen into helium, a process that releases vast amounts of energy and sustains the star's outward radiation pressure. In lower-mass stars like the Sun, this process proceeds steadily, taking billions of years to exhaust the hydrogen in the core. But our 136A1 is in a category of stars where the fusion process is so aggressive that hydrogen is depleted in a mere couple of million years. Once that fuel is exhausted, the core will contract under gravity, temperatures will rise even further, and a cascade of heavier element fusion, helium, carbon, oxygen, and possibly beyond, will briefly extend the star's life. But these later stages are measured in thousands, not millions, of years. This rapid consumption leads to internal instability. The star must constantly adjust to changes in its core, balancing the gravitational collapse with the energy generated by fusion. In massive stars like our 136A1, this delicate balancing act becomes increasingly precarious as the fusion process races through the elements. And with each step, the risk of catastrophic failure increases. Unlike lower-mass stars, which end their lives gently, swelling into red giants and eventually shedding outer layers to leave behind a white dwarf, our 136A1's demise will be anything but peaceful. It's likely headed toward an explosive and transformative end. But even before that final moment arrives, its short lifespan profoundly affects its surroundings. Massive stars like this shape the evolution of entire galaxies. Their intense radiation, strong stellar winds, and eventual supernova explosions inject energy into the interstellar medium, compressing gas clouds and triggering the next wave of star formation. This creates a sort of poetic symmetry. Stars like our 136A1 live fast and die young, but their deaths plant the seeds for new generations of stars and, ultimately, the elements that make planets, atmospheres, and life. Their short lives are the catalyst for long-term cosmic change. It's worth noting that our understanding of our 136A1's life cycle is still evolving. Because so few stars of this mass exist, at least, as far as we can currently observe, there's considerable uncertainty about their internal dynamics. Some researchers believe that these stars might be even more unstable than current models suggest, perhaps leading to unusual modes of death, such as parent stability supernovae or direct collapse into black holes without a traditional explosion. In any case, our 136A1 is already burning out. Its internal pressures and fusion processes are driving it inexorably toward its end. Its birth was recent in cosmic time, and its death will arrive in what amounts to the next heartbeat of the universe. And when it does go, it will mark the end of one of the most extraordinary stellar chapters we've ever witnessed. What's most striking about our 136A1's lifespan isn't just how short it is, it's what it manages to do in that short time. It outshines, outpowers, and outburns nearly every other star in the universe. In just a few million years, it will leave behind more of a legacy than many stars do in 10 billion. Its brief existence is a spectacle, a cosmic firework that illuminates not only its nebula but our understanding of what stars can be. And so, our 136A1 reminds us, brilliance and longevity don't always go hand in hand. Sometimes the most impactful forces in the universe are those that burn the brightest and vanish the fastest. If the sheer mass and brightness of our 136A1 weren't enough to secure its place as one of the most extreme stars in the cosmos, its surface temperature would still make it a cosmic outlier. This star isn't just massive and luminous, it is scorching in a way that defies intuition. With a surface temperature exceeding 50,000 Kelvin, our 136A1 is one of the hottest stars ever observed. To put that into perspective, the surface temperature of our own Sun is around 5,778 Kelvin. That means our 136A1 is nearly 9 times hotter at the surface than the Sun, and it shows. When most people imagine a hot object, they often think of red, orange, or yellow colors, like a flame or molten metal. But stars don't follow this intuitive path. As the temperature increases, the color shifts along the electromagnetic spectrum. Cooler stars appear red or orange, medium-temperature stars like the Sun appear yellow-white, and hotter stars shine white or even blue. Our 136A1 falls at the extreme blue end of this scale, glowing with a searing, bluish-white light that radiates in not just visible light, but also in ultraviolet wavelengths invisible to the human eye. In fact, a significant portion of its output is in high-energy UV radiation, making it dangerous and deadly to anything near it, if planets could even exist around such a monster. But what does such a high temperature mean in the physical sense? It indicates that the star's outer layers are in a state of extreme excitation, where atoms are constantly being stripped of their electrons due to the intense energy environment. This is one reason our 136A1 has been classified as a wolf-rayet star, a rare and short-lived type of star defined by extremely high surface temperatures and strong stellar winds that blow off its outer layers. These stars are essentially exposed stellar cores, having already shed much of their hydrogen envelope, exposing the helium and heavier elements within. At over 50,000 K, our 136A1's temperature drives insane fusion rates in its core, which then push outward with incredible radiation pressure. But more than just powering its light, this heat fuels violently fast stellar winds, outflows of ionized particles traveling at speeds of thousands of kilometers per second. These winds are strong enough to strip material off the star at an astonishing rate. Our 136A1 loses mass through its winds far more quickly than a typical star. Some estimates suggest it ejects mass equivalent to Earth's weight every few hours. That's how violent and turbulent this star's atmosphere is. Moreover, the blistering surface temperature plays a direct role in how the star interacts with its environment. Our 136A1 doesn't simply light up the Tarantula Nebula like a giant bulb, it sculpts it. Its ultraviolet radiation ionizes surrounding hydrogen gas, causing it to glow in stunning, colorful displays. These emissions are what make the Tarantula Nebula one of the brightest and most active star-forming regions in the local group of galaxies. Without stars like our 136A1, the nebula would be a dark, quiet cloud of dust and gas. But with it, it becomes an illuminated furnace, a stellar nursery and a cauldron of cosmic activity. That said, temperatures this high are not easy to measure directly. Determining the surface temperature of a star like our 136A1 involves complex spectral analysis, where astronomers examine the light coming from the star and split it into its component wavelengths. By studying the absorption and emission lines in the spectrum, specifically those associated with ionized helium, nitrogen, carbon, and oxygen, scientists can deduce the temperature, composition, and structure of the star's atmosphere. These observations are often made using space-based telescopes like Hubble, or ground-based observatories like the Very Large Telescope, VLT, using adaptive optics to penetrate the haze of interstellar gas and resolve the individual stars within the R136 cluster. Even with these tools, it's not always easy. The extreme conditions surrounding R136A1 mean that its spectrum can be broadened, blurred, and blended with that of nearby stars in its densely packed cluster. Despite this, multiple studies have consistently found its effective temperature to lie in the range of 50,000 to 53,000 Kelvin. That's not only hot, it's beyond comprehension in human terms. At such temperatures, even metals would vaporize into plasma in a fraction of a second. Nothing solid, nothing familiar, nothing that resembles our earthly materials could exist. This extraordinary temperature also hints at R136A1's internal structure and its place in stellar evolution. Such heat is only possible in a star that is not only extremely massive but also highly evolved. While it may still be burning hydrogen in its core, a phase known as the main sequence, its outer layers have already been stripped or are in the process of being ejected, revealing the deeper, more volatile layers beneath. It's like watching a fire that's so intense it burns through its own fuel and starts devouring its foundation. And as it continues to age, R136A1's temperature may rise even further as it begins to fuse heavier elements, causing more contraction and ignition in its core. But ironically, the hotter it gets, the closer it comes to its own destruction. That's the paradox of massive stars. The more fiercely they burn, the more fragile their future becomes. Ultimately, R136A1's surface temperature is not just a number, it's a signature of power, a mark of instability, and a glowing signal that this star is living at the edge of what physics can explain. It is a laboratory in space, a place where atomic and subatomic interactions play out under the most extreme conditions imaginable. The heat it generates affects not just itself but its entire region of space. It's no exaggeration to say that R136A1's temperature shapes the fate of stars that haven't even formed yet, simply by how it energizes the cloud around it. It is, quite literally, the kind of heat that creates and destroys in equal measure. When we talk about luminosity in the universe, the sheer power of light and energy emitted by celestial bodies, we often use our sun as a benchmark. It makes sense. The sun, after all, is the most influential object in our solar system, bathing Earth in a steady stream of life-sustaining energy. But when you compare it to R136A1, the sun becomes a mere candle flickering beside a thermonuclear spotlight. R136A1 isn't just bright, it is unimaginably luminous, pumping out light and radiation at levels that almost defy comprehension. Estimates place the luminosity of R136A1 at over 8.7 million times that of the Sun. Some studies have pushed that figure even higher depending on the model and assumptions used. To give this some context, if R136A1 were somehow placed at the center of our solar system, replacing the Sun, it wouldn't just outshine our star, it would incinerate Earth and every planet out to at least Jupiter's orbit in an instant. The temperature across Earth's surface would rise to thousands of degrees almost immediately, and the planet's atmosphere would be stripped away by the intense ultraviolet radiation. In fact, space itself around R136A1 becomes altered by the sheer energy it emits, with interstellar gas and dust vaporized or blasted away by its blinding output. But where does this blinding luminosity come from? It all stems from the mass and temperature of the star. In the realm of astrophysics, there's a rough relationship known as the mass-luminosity relation. The more massive a star is, the disproportionately more luminous it becomes. But this isn't a simple linear curve. A star that's 10 times more massive than the Sun isn't 10 times more luminous. It's thousands of times more luminous. And when you scale that up to a star like R136A1, with over 200 solar masses, the result is a titanic, nearly uncontrollable output of radiant energy. This radiation is produced by nuclear fusion in the star's core. At its heart, R136A1 fuses hydrogen into helium at an extraordinary rate, releasing energy in the form of gamma rays. These high-energy photons take thousands of years to journey from the core to the surface, scattering and bouncing their way through dense layers of plasma. By the time they reach the surface, they've lost some energy, emerging as ultraviolet and visible light, but still at levels far beyond human comprehension. The total radiant energy is so intense that the very structure of the star is altered to accommodate it. Our 136A1 teeters on the edge of stability, its radiation so strong that it pushes against the force of its own gravity. Without this radiation pressure, the star would collapse inward under its own immense weight. The ultraviolet portion of its luminosity is especially noteworthy. Our 136A1 emits so much UV radiation that it sculpts the entire Tarantula Nebula around it, creating shockwaves and ionization fronts that shape stellar nurseries, trigger new star formation, and vaporize fragile interstellar materials. It's like a celestial sculptor, carving new shapes into space with pure energy. Entire clouds of gas light up in response to its presence, creating some of the most breathtaking nebular imagery ever captured by telescopes. This also raises an important point. Most of our 136A1's luminosity is invisible to the human eye. We perceive only a small sliver of the electromagnetic spectrum, primarily visible light. But our 136A1 shines even more powerfully in ultraviolet and soft X-ray wavelengths. Instruments aboard space telescopes like Hubble, Chandra, and the James Webb Space Telescope, JWST, are necessary to detect the full range of its radiative power. Through these observations, astronomers can model its energy output and track how its luminosity evolves over time. But luminosity isn't just a measure of brightness. It's a measure of power, how much energy a star emits every second. Our Sun produces about 3.8x10 superscript 2 watts of energy. That's already a number so vast it's difficult to wrap our heads around. But multiply that by 8.7 million, and you get a luminosity of more than 3x10 superscript 3 watts. That's more energy every second than all the electricity humans have ever generated, or ever will, in our entire history. If you were to somehow survive long enough to look directly at a 136A1 from a safe distance, it would outshine everything else in the sky. Yet from Earth, it's not visible without telescopes because of its incredible distance. Around 160,000 light-years away, nestled deep in the Large Magellanic Cloud. Even so, its radiation still reaches us, a ghostly whisper of the inferno happening far across the void. And it's not just light it sends out, it's also momentum. Radiation exerts pressure, and in the case of our 136A1, this radiation pressure is strong enough to blow off the star's own outer layers. It drives stellar winds, fast, powerful outflows of charged particles moving at thousands of kilometers per second. These winds carry the star's mass into surrounding space and help regulate its structure. Without such immense luminosity, these winds would be weak or non-existent. But a 136A1's brilliance makes them one of the defining features of its life. What's perhaps most astonishing is how this luminosity fits into the story of cosmic evolution. Massive, luminous stars like our 136A1 are the universe's cosmic engines. They forge heavy elements in their cores through fusion and scatter them into the cosmos when they die. Everything we are, carbon, oxygen, calcium in our bones, iron in our blood, was once part of a star like our 136A1. Its luminosity isn't just about light, it's about the story of matter itself, cycling through generations of stars, creating the building blocks for planets and life. And yet, this luminosity comes at a cost. A star that burns this brightly cannot burn forever. The energy that sustains its glow also accelerates its end. The very process that makes our 136A1 the most luminous known star is the same one that guarantees it will live a short, violent life. Our 136A1 shines not as a distant twinkle, but as a warning and a wonder, a testament to what the universe can create, and how such creation always walks hand in hand with destruction. In its glow, we see both the birth and the end of things. We see the furnace from which the universe builds, and the fire into which it will one day collapse. When astronomers first turned their spectroscopes toward our 136A1 and analyzed the light it emitted, what they found placed the star in a class unlike most others, a category reserved for the most intense, turbulent, and short-lived stars in the universe. Our 136A1 is classified as a wolf-rayet star, one of the rarest and most extreme spectral types known in stellar astrophysics. This classification doesn't just describe the color or surface temperature, it tells us something far deeper about the star's composition, structure, and its wild, fast-burning journey toward death. To understand why this matters, we need to dig into what it means to be a wolf-rayet star. The spectral classification system for stars traditionally goes from O, B, A, F, G, K to M, categories based on surface temperature and spectral features, with O-type stars being the hottest and most massive. But wolf-rayet stars are something else entirely. They represent a post-main sequence evolutionary stage of the most massive stars in the universe, and a 136A1, with its immense mass and blistering energy output, fits squarely into this elite group. More specifically, it's categorized as WN5H, a wolf-rayet subtype with unique characteristics. Let's break that down. The WN designation indicates that the star's spectrum shows prominent lines of ionized nitrogen, N, and helium, but a notable lack of hydrogen lines, at least under normal wolf-rayet conditions. However, the H at the end of WN5H tells us something very specific. Despite appearing as a wolf-rayet star, our 136A1 still retains some hydrogen in its outer layers. This makes it an extremely massive star that is still in the core hydrogen-burning phase, unlike classical wolf-rayet stars that have completely burned through their hydrogen and are fusing heavier elements like helium or carbon. This distinction is critical. While classical wolf-rayet stars are naked stellar cores, exposed after blowing off their hydrogen envelopes through powerful stellar winds, stars like our 136A1 are thought to be so massive that their intense radiation pressure preemptively strips their outer hydrogen layers while they are still burning hydrogen in their cores. That's what makes our 136A1 an oddity. It behaves spectrally like a post-main sequence star but is, in fact, still on the main sequence, just an extremely short-lived and energetic one. The spectral lines that define our 136A1 are broad and strong, indicating rapid outflows of stellar material. These lines are not shaped solely by temperature or composition, but also by motion, specifically, the velocity of stellar winds. Our 136A1 is ejecting material from its outer layers at speeds of over 2,000 to 3,000 kilometers per second. That's millions of tons of plasma being hurled into space every second. These winds are driven by the intense radiation pressure inside the star, a force so strong that it's nearly tearing the star apart as fast as it's holding it together. Wolf-rayet stars are rare by any measure. Out of the hundreds of billions of stars in the Milky Way, only a few hundred have been identified as wolf-rayet types. That's because only the most massive stars can become them, and even then, only briefly. Their evolutionary timeline is so compressed that you'd have to observe millions of stars to catch even a glimpse of one at the right time. Our 136A1, despite being in the Large Magellanic Cloud and not the Milky Way itself, is one of the clearest examples of this rare breed. Being a wolf-rayet star also means that our 136A1 is chemically enriched in ways that affect not only itself but its environment. The material it ejects into space is rich in helium, nitrogen, and possibly carbon and oxygen, depending on its exact evolutionary state. These enriched winds contribute to the chemical evolution of the surrounding nebula, seeding space with the building blocks of future stars and planets. In a way, our 136A1 is already giving back to the cosmos long before its final death throes. There's another important implication of this spectral classification. Because our 136A1 is essentially still burning hydrogen but showing wolf-rayet features, it provides a unique window into early stellar evolution for extremely massive stars. It challenges traditional ideas about the order and pacing of stellar phases. Normally, we expect hydrogen burning to be followed by envelope loss and wolf-rayet features, but our 136A1 appears to be doing it all at once, in a state of chaotic simultaneity. This has driven astrophysicists to revise models of stellar evolution for stars over 100 solar masses. Even the process of classifying our 136A1 as a wolf-rayet star was far from straightforward. Its location in the heart of the R136 cluster, surrounded by other massive stars, made it hard to resolve clearly. Early observations even debated whether it was a single star at all. But with advances in high-resolution spectroscopy and adaptive optics, astronomers were able to isolate its spectrum and identify the telltale signatures: broad emission lines from helium and nitrogen, high outflow velocities, and the unusual presence of hydrogen. And while the WN5H classification may look like a sterile label, it tells us so much. It reveals a star caught in an impossible act, burning with unimaginable intensity, shedding its own skin while still clinging to the core fuel of its youth, and living on the brink of collapse. R136A1 is not just another hot blue star. It's a prototype of the most extreme kind of stellar existence, a wolf-rayet monster that defies simplicity and demands explanation. It's also a reminder that even the tools we use to classify stars can fall short when faced with something as exotic as R136A1. This star blurs the lines between categories, mixes evolutionary stages, and refuses to fit neatly into any model. In doing so, it tells us not just about itself, but about the limitations of our knowledge, and the exciting promise of what we've yet to discover. In the heart of R136A1, an extraordinary and delicate battle is constantly unfolding, a war between two colossal forces that could not be more different, yet together, they define the very nature of the star. On one side is gravity, the fundamental force that pulls everything inward, trying to crush the star under the weight of its own unimaginable mass. On the other side is radiation pressure, the outward push of light and energy generated from within the core. This dynamic tension between collapse and expansion is not only what keeps R136A1 alive, it is what allows it to exist at all. Gravity is relentless. In a star as massive as R136A1, over 200 times the mass of our Sun, gravity is so powerful that, left unchecked, it would immediately collapse the star into a compact object, like a neutron star or black hole. However, the very act of nuclear fusion, the core process that fuels all stars, produces an enormous amount of energy. This energy, as it moves from the core toward the surface, doesn't just heat the star, it pushes outward, exerting pressure. This is radiation pressure, the force exerted by photons as they scatter and push against particles inside the star's layers. In most ordinary stars like the Sun, radiation pressure is a relatively small player. The Sun maintains equilibrium mostly through gas pressure, the thermal motion of particles keeping it from collapsing. But in R136A1, the story is entirely different. With such a massive core and so much energy being generated every second, radiation pressure takes the lead role. It becomes the dominant counterbalance to gravity, essentially acting as the internal scaffolding that keeps the star from imploding under its own weight. The pressure comes from the sheer volume of high-energy photons, mostly gamma rays, being produced through nuclear fusion. In a star like R136A1, hydrogen is being converted into helium at an astonishing rate through the Carnot cycle, which is more efficient at high temperatures and dominates in massive stars. This process produces far more energy than the proton-proton chain reaction that powers stars like the Sun. The result is a blinding storm of photons that exert a tremendous outward force. These photons don't just travel in straight lines out of the star, they scatter, they ricochet off ions and electrons, and this scattering applies force. In effect, the photons are constantly pushing outward against the immense pull of gravity. This is what keeps the outer layers of R136A1 from collapsing inward. It's like an internal pressure cooker with the lid held in place by sheer outward explosive force. But this balance is precarious, especially in a star as massive as R136A1. The closer a star gets to the so-called Eddington limit, the more unstable this balance becomes. The Eddington limit defines the maximum luminosity a star can have before radiation pressure overwhelms gravity, causing the outer layers to be blown off. R136A1 teeters dangerously close to, if not slightly beyond, this threshold. That means parts of its outer atmosphere are constantly being stripped away by the overpowering pressure of its own light. This is why R136A1 exhibits such powerful stellar winds, with mass loss rates so high that it's shedding significant portions of itself over time. These outflows are not just a side effect. They are a direct result of the star's radiation pressure attempting to exceed the limits of gravitational containment. The photons are so numerous and energetic that they are literally driving the star apart, molecule by molecule, second by second. Despite this, the star remains remarkably stable in shape, not because it's rigid, but because of a state of hydrostatic equilibrium. This is the term astronomers use to describe the finely tuned balance where the inward pull of gravity is exactly matched by the outward push of radiation pressure at every layer of the star. In our 136A1, this equilibrium is far more fragile than in smaller stars. A slight increase in fusion rate or core temperature could tip the balance and blow the star apart. A slight decrease, and the crushing force of gravity would take over. It's a cosmic tightrope walk, and our 136A1 has been walking it since birth. There's another fascinating consequence of radiation pressure at these extremes: the inflation of the star's outer layers. Because radiation is constantly pushing outward with such intensity, the outer envelope of the star becomes extended and diffuse. Our 136A1's atmosphere isn't compact or neatly layered, it's bloated, unstable, and semi-transparent, with the very definition of its surface becoming a bit fuzzy. The radius of the star becomes hard to measure precisely because its surface is more like a gradation of densities and temperatures rather than a clean edge. This also impacts the appearance of the star's spectrum. The strong, broad emission lines characteristic of wolf-rayet stars are not just signs of high temperatures, they're markers of this inflated, chaotic outer atmosphere where high-velocity winds, radiation pressure, and complex ionization states collide to create dramatic signatures of instability. And then there's the deeper implication: radiation pressure is not just a stabilizing force. It is also a destructive one. In attempting to keep the star intact, it's also accelerating its demise. Every second, our 136A1's core produces so much energy that it threatens to blow the star apart. Radiation pressure makes it possible for the star to survive, but it also drives the very mechanisms, mass loss, energy drain, and stellar winds, that shorten its life dramatically. So, the role of radiation pressure in our 136A1 is one of cosmic irony. It is the glue that holds this hypermassive star together, and the dynamite that will eventually tear it apart. It sustains life, but only for a fleeting moment in astronomical terms. A few million years at best. Understanding this mechanism helps scientists probe the upper limits of star formation. It raises fundamental questions. How massive can a star truly be before radiation pressure prevents it from forming at all? How does this force shape the early evolution of galaxies? And what happens when radiation pressure is no longer strong enough to keep gravity at bay? In our 136A1, we see all these questions embodied in a single, impossible star. A furnace of light held together by the very energy it seeks to release, a celestial paradox suspended between stability and catastrophe. At the heart of our 136A1, the core is a maelstrom of unimaginable intensity. Temperatures soar to tens of millions of degrees Kelvin, and pressures are so immense that the normal behavior of matter completely breaks down. Here, hydrogen, the most basic and abundant element in the universe, is being crushed and fused into helium in a process that not only fuels the star's light but defines its very lifespan. But unlike stars like our Sun, which sip hydrogen over billions of years in a slow and steady burn, our 136A1 devours it with ferocious speed, like a cosmic wildfire racing through a forest of nuclear fuel. The process through which our 136A1 burns its hydrogen is a more advanced and more aggressive mechanism than what happens in smaller stars. In our Sun, the dominant fusion mechanism is the proton-proton chain, which fuses hydrogen nuclei, protons, into helium slowly and gradually. But in stars with masses greater than around 1.3 times that of the Sun, the dominant fusion process is the CNO cycle, and in a star as massive as our 136A1, the CNO cycle operates in overdrive. The CNO cycle, carbon, nitrogen, oxygen cycle, is a catalytic fusion process where hydrogen nuclei are converted into helium using carbon, nitrogen, and oxygen as intermediaries. The remarkable aspect of the CNO cycle is that it's extremely temperature sensitive. The rate of fusion increases dramatically with even small increases in temperature. In R136A1, where the core temperature likely exceeds 60 million Kelvin or more, the CNO cycle is raging at maximum capacity. This intense fusion process means R136A1 is converting vast quantities of hydrogen into helium every second. Just to put things into perspective, the Sun converts about 600 million tons of hydrogen into helium every second and emits energy equal to about 3.8 times 10 superscript 2 watts. R136A1, being millions of times more luminous, is burning through its hydrogen at a rate orders of magnitude greater. Estimates suggest possibly tens of billions of tons per second. This tremendous rate of fusion not only sustains its extreme luminosity and heat but also drastically shortens its lifespan. In stellar terms, R136A1 is living fast and dying young. Because of this furious pace, R136A1 is expected to live only about 1.5 to 2 million years. Compare that with the Sun's projected lifespan of around 10 billion years, and you begin to appreciate just how fast this star is racing toward its end. It's like comparing a flash of lightning to the slow drip of a glacier. While the Sun will spend billions of years gently sipping away at its hydrogen, R136A1 is an inferno, churning through its fuel with reckless abandon. The structure of the core in R136A1 is also radically different. The incredible temperatures and densities ensure that the plasma inside is completely ionized. Protons and electrons are stripped apart, existing in a chaotic state where electromagnetic interactions are extreme and fusion occurs at staggering rates. The pressure from this activity must be contained, and that's where the earlier discussed radiation pressure comes in, preventing collapse, but just barely. The balance is so delicate that any significant increase in energy output could destabilize the entire star. But the story doesn't end with hydrogen. As R136A1 burns through its core hydrogen, it will begin to enter later stages of stellar evolution, eventually fusing helium into carbon, carbon into oxygen, and so on, progressing through heavier elements in a cascading series of nuclear reactions. However, each subsequent stage is dramatically shorter in duration than the one before. While hydrogen fusion may last a couple million years, the helium-burning phase may last only hundreds of thousands of years, and the final iron core collapse could take mere days. Another critical consequence of such a rapid burn rate is the buildup of helium and other heavier elements in the core, which leads to structural changes in the star. The helium, ash from hydrogen fusion sinks inward, increasing core density and pressure. As this continues, the star becomes increasingly unstable, as gravity begins to outweigh the diminishing radiation pressure. Eventually, this will lead to the star's collapse, a subject we'll discuss in detail in upcoming segments. But for now, it's enough to know that every fusion reaction in R136A1 is another step toward its inevitable end. There's also an environmental impact to this furious fuel consumption. R136A1's powerful stellar winds, driven by both radiation pressure and fusion-driven instability, are ejecting material into the surrounding Tarantula Nebula. These outflows are rich in fusion byproducts like helium, nitrogen, and even trace amounts of heavier elements. Over time, R136A1 becomes not only a source of light and heat, but also a chemical polluter, enriching its surroundings and influencing the birth of future stars. This process has significant implications for galactic evolution. Massive stars like R136A1 act as cosmic furnaces, generating the heavy elements that seed the next generation of stars and planets. Without stars like it, elements like carbon, oxygen, and nitrogen, essential for life, would be vanishingly rare. Though rare and short-lived, massive stars are fundamental to the chemical evolution of the universe. The ferocity with which R136A1 consumes hydrogen also serves as a constraint on the upper limits of stellar mass. The faster a star burns fuel, the less time it has to live, and the more unstable it becomes. This makes astronomers question, is there a point where a star becomes so massive that it burns itself out before it can even be fully born? Stars like R136A1 test these boundaries and force scientists to continuously adjust their models. It's a strange paradox. R136A1's life-sustaining energy is also the root of its instability and eventual death. Every fusion reaction buys it time, but also moves it closer to oblivion. In its core, atoms are smashed together in an endless cycle of destruction and creation, keeping the star alive while also shaping the fate of the universe around it. So when we speak of R136A1's fusion process, we're not just talking about the heat and light of a distant star. We're witnessing the furious heartbeat of a cosmic giant, a nuclear titan consuming itself in a burst of glory, destined to blaze brilliantly for a moment, and then vanish into the fabric of the universe. The inevitable fate of R136A1 is a topic that captures the imagination of scientists and stargazers alike, not just because of its dramatic possibilities, but because it touches the very core of what we know, and don't know, about how the universe ends things. When a star burns this hot, this bright, and this fast, the question isn't if it will explode, it's how. R136A1 is destined for destruction. But the nature of that destruction is something we're still trying to understand. Will it go out in a spectacular supernova? Will it tear itself apart in an even more violent hypernova? Or could it vanish into darkness, collapsing into a black hole with barely a whisper of its passing? The answers lie in the physics playing out deep within its core, and in the fragile balance of mass, energy, and time. A supernova is the explosive death of a massive star, a cosmic detonation so powerful that it can briefly outshine an entire galaxy. Most stars that end their lives in supernovae have masses in the range of about 8 to 20 times that of the Sun. For those stars, the end comes when nuclear fusion can no longer support the core. When fusion creates iron, the element with the most tightly bound nucleus, energy can no longer be extracted through fusion. Instead, fusion stops, gravity wins, and the core collapses in on itself in a fraction of a second. The resulting rebound creates a shockwave that blasts the star's outer layers into space in a tremendous explosion. But R136A1 is not like most stars. It is so massive, so extreme, that it may not follow the usual path to a core collapse supernova. With an initial mass estimated to exceed 200 times that of the Sun, R136A1 may actually bypass traditional supernova mechanisms and instead face a more exotic, catastrophic demise. The possibilities fall into a few different categories, each more dramatic than the last. One likely outcome is that R136A1 will go supernova in the classical sense, but as a type IB or type IC supernova. These types occur when the star has lost its outer hydrogen layer, and in some cases, the helium layer too, which is common for wolf-rayet stars like R136A1. In this case, the supernova would lack the usual hydrogen lines in its spectrum, distinguishing it from a Type II supernova. However, even within the realm of core collapse supernovae, R136A1 would be an outlier. The energy of the explosion could be far greater than that of a typical core collapse event. But that's just the beginning of what might happen. Because of its enormous mass, R136A1 is also a candidate for what's known as a parent stability supernova, a rare and extreme type of explosion theorized to occur in stars with initial masses between about 140 and 260 solar masses. In this scenario, the temperature in the star's core becomes so high, reaching into the hundreds of millions of degrees, that gamma rays start spontaneously converting into electron-positron pairs. This reduces the radiation pressure that had been keeping gravity in check. Suddenly, the core becomes unstable and collapses, leading to a thermonuclear runaway reaction that completely obliterates the star. In a parent stability supernova, there is no remnant left behind, no black hole, no neutron star, nothing. The star is completely annihilated in a single apocalyptic flash. Whether R136A1 meets the conditions for a true parent stability event is still an open question. Some models suggest it may have shed enough of its initial mass through stellar winds that it might fall below the necessary threshold. Others argue that even if its current mass is lower, its original mass at birth could still make it a candidate. If R136A1 does die in this way, it would be a spectacular and extremely rare event, the kind of explosion we have never yet witnessed with certainty, but hope to catch someday with the next generation of space telescopes. Another possibility is the star will undergo a hypernova, a supernova on steroids. A hypernova is typically associated with stars that collapse directly into a black hole, releasing 10 times the energy of a normal supernova. These events are often accompanied by long-duration gamma-ray bursts, which are some of the most energetic phenomena in the universe. For a hypernova to occur, the collapsing core must retain enough angular momentum to form an accretion disk around the newly born black hole. This disk can then power jets of material moving at nearly the speed of light, jets that can punch through the star and blast out into space in brilliant beams of gamma radiation. Given our 136A1's immense size and power, some scientists speculate that it could become one of the most violent hypernovae ever seen. If it were to die in this fashion, it could release as much energy in a few seconds as the Sun will emit over its entire 10 billion-year lifetime. It's the kind of event that could briefly rival the brightness of a galaxy, and leave behind a massive black hole as a cosmic monument to the star's life. Of course, not all endings are so flashy. There's also the possibility that our 136A1 could collapse directly into a black hole, skipping the explosion altogether. In some theoretical models, if the core becomes massive enough and fusion stops too suddenly, the entire star could collapse inward at once. In this case, gravity would overcome all other forces, and no explosion would occur, just a sudden, silent implosion into darkness. We might only know it had died because the light suddenly disappeared. No grand finale, no blast wave, no remnant, just a void. Whatever the final path, one thing is certain. Our 136A1 is a ticking time bomb, and its death will not be a quiet one. Whether it tears itself apart in a titanic explosion, collapses in a gamma-ray-fueled fury, or disappears into a black hole, its demise will echo across the cosmos in a way that few events can rival. And when it does die, it will seed the surrounding universe with heavy elements, oxygen, silicon, sulfur, and perhaps even iron, feeding the next generation of stars and planets with the material necessary for life itself. Its explosive fate isn't just an end, it's a cosmic rebirth. As we push deeper into the apocalyptic future of our 136A1, one outcome grows increasingly likely with every heartbeat of its burning core: collapse into a black hole. But the nature of that collapse, its violence, its legacy, and whether it will light up the cosmos or vanish without a trace, still stirs intense speculation. What kind of black hole could emerge from such a monster? Could the death of our 136A1 trigger a hypernova, one of the most violent explosions in the universe? Or might it transcend even that fate, hinting at something more exotic, something that challenges the very fabric of physics? To begin with, the black hole scenario is the most straightforward and widely accepted fate for a star as massive as our 136A1. With an initial mass exceeding 200 times that of the Sun, even after shedding a significant amount of material through powerful stellar winds, this star is almost certainly massive enough to produce a stellar mass black hole once its fusion engine shuts down. At the end of its life, when it can no longer fuse elements to resist the pull of gravity, the core will collapse catastrophically. If the mass remaining in the core exceeds the Tolman, Oppenheimer, Volkoff limit, which is around 2 to 3 solar masses, then not even neutron degeneracy pressure will be enough to halt the collapse. The star's core will cave in upon itself, forming a singularity, a region of space where gravity is so intense that not even light can escape. But the scale of our 136A1's potential collapse elevates the black hole possibility beyond the ordinary. If the final core mass is massive enough, which it likely will be, it might not just produce an ordinary black hole of 5 to 10 solar masses, like many we detect in binary systems. Instead, it could give rise to an intermediate mass black hole, a hypothetical class of black holes with masses between 100 and 100,000 solar masses. These elusive objects may be the missing link between the stellar mass black holes formed from normal stars and the supermassive black holes that sit at the centers of galaxies. And our 136A1, by virtue of its incredible mass, might be one of the few known stars capable of becoming one. Now, how does a hypernova factor into this? A hypernova is a type of supernova that is 10 or more times more energetic than a typical core collapse explosion. Unlike a standard Type II or IB/C supernova, a hypernova involves stars with high angular momentum and enormous mass. In the hypernova model, the collapsing core doesn't simply implode into a black hole and stop. Instead, as the star collapses, it forms an accretion disk of high-energy material swirling around the new black hole. The energy released by the infall of this matter is so intense that it can power powerful relativistic jets, twin beams of matter and radiation that blast outward at near-light speeds. These jets can tear through the star's outer layers, blasting them into interstellar space and creating one of the most luminous events the universe can produce. Such jets are often thought to be the source of long-duration gamma-ray bursts, which can last several seconds and release more energy than our Sun will emit in its entire life. If our 136A1 ends in a hypernova, the explosion would likely be accompanied by one of these titanic gamma-ray bursts, visible across the cosmos, and potentially detectable here on Earth, even from 160,000 light-years away. There's an eerie thought here. Had our 136A1 been pointed just right, and had it been much closer to Earth, a gamma-ray burst from its death could have posed a real threat to life on our planet. Gamma-ray bursts are capable of stripping away the ozone layer and causing mass extinctions if they occur within our galaxy and direct their beams toward us. Thankfully, our 136A1 lies safely in the Large Magellanic Cloud, well beyond the danger zone. But for scientists, what makes our 136A1 so compelling isn't just the hypernova possibility or the black hole endgame. It's the rare chance to study an object that might push beyond either of those. Some researchers have speculated about even more exotic outcomes, especially if our 136A1 continues to challenge mass thresholds. Could it become something truly unprecedented? One such speculative outcome is a direct collapse into a black hole with no explosion at all. In this case, the star's core would collapse and consume the rest of the star in a matter of seconds, emitting few visible signals. No supernova. No hypernova. Just silence. This is sometimes called a failed supernova, and several potential candidates have already been observed, massive stars that seem to disappear from the sky without any visible bang. Our 136A1 could become the ultimate example of this phenomenon, its death detectable only through neutrino emissions or the sudden absence of its intense light. Another mind-bending possibility lies in the realm of quantum gravity and exotic compact objects. While still highly theoretical, some physicists speculate that extreme mass collapses might form something beyond a black hole, like a gravistar, boson star, or even a naked singularity. These are fringe theories, but they become harder to ignore when dealing with a star as colossal as our 136A1. If any star were to test the limits of general relativity, it's this one. Some theorists even wonder if stars like our 136A1 could be progenitors of primordial black holes, ancient relics from the early universe that might seed the growth of supermassive black holes and galaxy cores. While our 136A1 is not ancient, it represents the scale of collapse needed to explore those mechanisms in modern astrophysics. It gives us a kind of laboratory for studying what happens when matter is concentrated to extremes. Ultimately, the exact fate of our 136A1 may depend heavily on how much mass it loses before death. Stellar winds, especially in hot, massive stars like wolf-rayets, can strip away a significant percentage of mass over time. If our 136A1 loses too much, it may no longer qualify for a hypernova or intermediate mass black hole. But if enough of its core remains intact, and its spin is high enough, it could still deliver a cosmic firework of unparalleled magnitude. Whatever happens, the death of our 136A1 will not be a quiet closing chapter. It will be a violent punctuation mark in the life of the universe. Whether it ends in a brilliant flash that ripples across the cosmos or collapses into perfect silence, its fate will be among the most extraordinary events modern astronomy has the potential to witness. The scarcity of stars like our 136A1 in the universe is not just a matter of distance or visibility, it's a fundamental consequence of how the cosmos is built. The laws of physics, the nature of matter, and the violent processes of star formation all conspire to make stars this massive extraordinarily rare. When we look up into the sky and count the countless stars visible even with the naked eye, almost all of them fall into a much smaller mass range. Giants like our 136A1 stand apart, not only because of their immense size and luminosity, but because they form under incredibly specific, and incredibly rare, conditions. First, we must understand that the distribution of star masses in the universe follows a rule known as the initial mass function, IMF, first proposed by Edwin Salpeter in 1955. According to this rule, the universe forms far more low-mass stars than high-mass ones. For every massive star like a 136A1, there are tens of thousands, or even hundreds of thousands, of small stars like red dwarfs. In essence, nature seems biased toward creating smaller, more stable stars that can burn for billions of years. Massive stars, by contrast, are brief, violent phenomena, flashes in the cosmic pan. The reason for this preference lies in the physics of gravitational collapse. To form a star, a dense region of a molecular cloud must collapse under its own gravity. For small stars, this process is relatively common. But for a massive star to form, one with over 100 times the mass of the Sun, or in our 136A1's case, more than 200, the collapsing cloud must have a tremendous amount of gas and dust all compacted in the same region, and that material must collapse quickly before it's blown apart by radiation pressure and stellar feedback. Here's the problem: massive stars emit powerful radiation even while they are still forming. As they gather mass and begin to fuse hydrogen in their cores, they generate intense ultraviolet radiation and stellar winds that push outward with incredible force. This radiation can literally blow away the material still trying to fall onto the forming star, effectively cutting off its growth. This feedback mechanism sets a natural upper limit on how massive a star can become, making stars like our 136A1 statistical anomalies. In theory, this limit was long thought to be around 100 to 150 solar masses, until our 136A1 came along and shattered that ceiling. Another crucial factor is the environment in which these stars form. Our 136A1 didn't arise in isolation, it emerged from a dense, active star-forming region within the R136 cluster at the heart of the Tarantula Nebula, itself located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This region is a stellar nursery on steroids, packed with enough raw material and gravitational compression to overcome the feedback limitations that would stop star formation elsewhere. The Tarantula Nebula contains some of the most extreme conditions known to astrophysics, including shock waves from previous supernovae, supersonic turbulence, and incredibly high gas densities, all contributing to the rare birth of ultramassive stars. The metallicity of the environment also plays a role. In astrophysics, metals refer to any element heavier than helium. High metallicity environments tend to produce stars that shed more mass through stellar winds, while low metallicity environments allow stars to retain more of their mass as they evolve. The Large Magellanic Cloud has slightly lower metallicity than the Milky Way, which may have helped a 136A1 grow larger by losing less mass during its formation and early evolution. In essence, it was born in a sweet spot, dense enough to form, but metal poor enough to retain much of its initial mass. But even in ideal conditions, the formation of a star like our 136A1 is a cosmic balancing act. Slight variations in the local gravitational field, turbulence in the gas cloud, or radiation pressure from nearby stars can completely disrupt the process. Most of the time, those factors win, and the material fragments into several smaller stars rather than coalescing into a single gigantic one. This is why simulations of star formation rarely produce stars beyond 150 solar masses without extreme, finely tuned conditions. There's also the matter of timescale. Stars like our 136A1 live fast and die young. They burn through their nuclear fuel in just a few million years, an eye blink on cosmic timescales. In contrast, red dwarfs can live for hundreds of billions of years, meaning they accumulate over time, vastly outnumbering their massive counterparts. Even if the universe formed a million or 136A1-like stars in the past, most of them would already be dead. Their short lifespans make them even harder to detect because the window during which we can observe them is incredibly narrow. The rarity of such stars is also reflected in our observational records. Despite advanced telescopes scanning billions of stars across the night sky, our 136A1 remains one of only a tiny handful ever found to be this massive. Most supermassive stars we observe don't reach even close to 200 solar masses. And because stars this large are so luminous, we would likely spot them if they were nearby or even in neighboring galaxies. The fact that we haven't suggests just how few there are. Some astronomers have even proposed that a 136A1 may not be a single star at all. There's ongoing debate over whether what we see as one point of light is actually a tight binary or multiple star system, with two or more massive stars orbiting so closely that they appear as one. If this were the case, the rarity of true R136A1-like objects would be even greater than currently believed. However, the most recent high-resolution observations using instruments like the Very Large Telescope's interferometry system have increasingly supported the conclusion that R136A1 is indeed a single star, not a cluster or binary. This conclusion only makes its existence more astonishing. In the grand scheme of things, the universe prefers stability, and massive stars are anything but. They are explosive, volatile, and inherently self-limiting. Their formation is rare, their lifespans brief, and their deaths violent. The cosmos is filled with small, dim stars quietly burning for billions of years, while giants like our 136A1 blaze like torches and vanish before the universe can blink. This rarity is precisely what makes our 136A1 so valuable to scientists. It's not just an astronomical curiosity, it's a window into an extreme regime of astrophysics. It gives us a glimpse of what happens when the rules of star formation are pushed to their limits. Every new insight from our 136A1 helps refine our understanding of how stars form, how galaxies evolve, and how the universe recycles matter through creation and destruction. When astronomers first began closely observing our 136A1, its sheer brightness and mass sparked immediate debate. Was it truly a single, colossal star? Or could it instead be a trick of distance and resolution, perhaps a very tight group of massive stars masquerading as one? This question has not only intrigued the astrophysical community, but also cast a spotlight on the technological limits and interpretive challenges involved in studying distant, densely packed stellar environments. The cluster R136, located in the heart of the Tarantula Nebula, is one of the most massive and compact stellar nurseries known. It is brimming with young, hot stars, many of which are tens of times more massive than our Sun. In such an environment, stars are packed together incredibly closely, sometimes with only a fraction of a light-year between them. That's far tighter than the average interstellar distances we observe around our Sun, which can span multiple light-years. When viewed from Earth, even with high-powered telescopes, individual stars in these tight clusters can blend together, especially if they are close enough and shining brightly. This blending effect, what astronomers call an unresolved source, can easily make two or more stars appear as a single point of light. This ambiguity triggered speculation about our 136A1's true nature. Could it be a binary star system, two massive stars orbiting each other so tightly that our current telescopes see them as one? Or maybe even a multiple star system, with three or more giants caught in a gravitational dance? These are not idle questions. The implications are enormous. If our 136A1 is really two or more stars, then each would have a lower individual mass, and the theoretical ceiling for single-star mass would remain intact. If it's just one star, then it punches a hole in our current models, proving that stars can get more massive than most formation theories allow. To investigate this, astronomers turn to increasingly sophisticated tools. The Hubble Space Telescope, with its impressive optical capabilities and sharp resolution, was the first to seriously examine the region and identify our 136A1 as an exceptionally bright source. But even Hubble, orbiting hundreds of kilometers above Earth's atmosphere, faced limitations in resolving individual components in such a dense region 160,000 light-years away. It was possible that Hubble's resolution still blurred multiple stars into one image. Enter the Very Large Telescope, VLT, in Chile, equipped with adaptive optics and interferometric instruments that compensate for the atmospheric distortion that plagues Earth-based observations. The VLT's instruments, especially the sphere and gravity instruments, pushed the boundaries of resolution to unprecedented levels. These tools allowed astronomers to look even more closely at a 136A1, analyzing subtle variations in light and movement that would indicate the gravitational wobble characteristic of binary or multiple systems. What they found was nothing short of revolutionary. Despite the overwhelming odds and the densely packed stellar background, the most recent high-resolution observations suggest that a 136A1 is indeed a single, massive star. These studies, such as those conducted using the European Southern Observatory's VLT interferometer, managed to measure the angular diameter of our 136A1 with unprecedented precision. While there remains some uncertainty, the evidence is now strongly tilted toward the single-star hypothesis. One of the key pieces of evidence comes from spectroscopy, the study of light coming from the star, broken into its component wavelengths. In a binary or multiple system, especially one made of stars with slightly different compositions or temperatures, astronomers would expect to see variations or duplications in spectral lines, indications of more than one set of elements being observed, moving at different velocities. Instead, the spectral profile of our 136A1 appears consistent with a single source. The lack of noticeable Doppler shifts, changes in the star's light spectrum due to orbital motion, is another argument against it being a binary. If there were two stars orbiting each other, especially stars of such enormous mass, we would expect to see significant shifts in their spectra as they tugged on each other. But these aren't present. That said, skepticism still exists. Some astrophysicists remain cautious, pointing out that tightly bound binaries or stellar mergers might avoid detection with even our best instruments, especially at such extreme distances. There's also the possibility of an unresolved companion star so faint compared to our 136A1 that it's drowned out in the glare. But even this scenario would still leave our 136A1 as a single star far more massive than previously thought possible. This leads to another compelling idea: stellar mergers. In a densely packed environment like our 136, stars often interact gravitationally. Two massive stars in a close binary could spiral into each other over time and merge, forming a single supermassive star. If our 136A1 is the result of such a merger, it would still be considered a single star today, though its origins would be rooted in a violent and chaotic past. This idea neatly sidesteps the traditional mass limit problem. Instead of forming as a single 200-plus solar mass star, it formed from the fusion of two or more smaller stars. But again, observational evidence for this is lacking. No clear indicators, such as an expanding shell of gas from a recent collision, have been detected. Whether formed through a singular gravitational collapse or a high-energy merger, our 136A1 challenges everything we thought we knew about how stars form. If it's truly a single star, and the current evidence supports that it is, then it defies the theoretical models that place a hard upper limit on stellar mass. It suggests that in rare environments, with just the right conditions, the universe is capable of crafting stars of nearly inconceivable size and power. The debate over our 136A1's multiplicity has also fueled broader inquiries into how we define and detect stellar limits. If observational precision can still leave room for doubt at this level, how many other massive stars in other galaxies might be misclassified? Are we systematically underestimating the number of supermassive stars simply because we lack the resolution to discern their true nature? Whether our 136A1 is truly alone or hiding a twin, its story is one of scientific humility and wonder. It reminds us that our tools, as advanced as they are, still face limits, and that the cosmos remains full of surprises. For now, the prevailing view is that our 136A1 is not a binary, not a triplet, not a blended cluster masquerading as one light. It is, as best as we can tell, the most massive single star humanity has ever seen. The formation of our 136A1 remains one of the most intriguing and hotly debated topics in stellar astrophysics. Creating a star over 200 times the mass of the Sun pushes the boundaries of what our current models of star formation suggest is even possible. This isn't just a case of a big star forming like any other, only on a grander scale, our 136A1's existence forces us to reconsider the very mechanisms that sculpt stars from cosmic dust and gas. To understand how it may have formed, we have to explore several competing theories, each as fascinating as it is incomplete. The standard model of star formation begins with a molecular cloud, a cold, dense region of gas and dust where gravitational instabilities allow parts of the cloud to collapse under their own weight. As the collapsing region pulls in more material, it heats up and eventually ignites nuclear fusion at its core, becoming a protostar. Over time, it accumulates mass from the surrounding cloud, growing larger and hotter until it shines as a full-fledged star. But here's the problem. This process seems to hit a ceiling long before reaching 200 solar masses. Why? Because of radiation pressure, a force that becomes a critical player in the birth of massive stars. As a protostar gets more massive, it becomes more luminous, and the sheer pressure from the radiation it emits begins to push back on the infalling material. At a certain point, around 100 to 150 solar masses, according to most models, this pressure is thought to become so intense that it halts further accumulation of gas. In other words, the star prevents itself from growing any bigger. So how did a 136A1, clocking in at over 200 solar masses, manage to sidestep this cosmic self-limitation? One leading idea is that a 136A1 may have formed through competitive accretion in a very special kind of environment. In a dense star cluster like a 136, hundreds or even thousands of protostars are forming simultaneously in close proximity. These baby stars jostle for mass, pulling material from the same surrounding gas cloud. In this environment, some stars may gain a gravitational advantage, perhaps by forming in slightly denser regions or closer to the center of the cloud, and begin to grow much faster than their neighbors. These winning stars can dominate the accretion flow, sucking in far more material than they could in isolation. In the extreme case of our 136A1, it might have experienced runaway growth during this competitive phase, gobbling up so much gas before radiation pressure could catch up that it blew past the theoretical mass limit. A variation of this model involves stellar mergers. In tightly packed young clusters like our 136, stars aren't just close together, they can actually collide. If two massive protostars orbiting each other spiral inwards, or if chaotic gravitational interactions sling them into each other, they can merge and form a single, supermassive object. This scenario would explain how a 136A1 could have become so massive despite the radiation barrier. It didn't accrete all its mass in one steady process. It violently fused with one or more sibling stars. This possibility gains further traction when you consider the incredibly short lifespans of such massive stars. If a 136A1 formed via a merger just a few million years ago, it wouldn't have had time to evolve into a more stable or cooler star, and it would still be in its hot, luminous, short-lived prime. Another, more speculative theory suggests that the original gas cloud was unusually massive and dense, and conditions were just right for direct monolithic collapse, meaning our 136A1 formed directly as one enormous protostar without fragmenting into smaller pieces. Normally, when a gas cloud collapses, turbulence and density variations cause it to break apart into multiple fragments, each of which forms its own star. But if the temperature, pressure, magnetic fields, and angular momentum are tuned just right, it's theoretically possible for the entire cloud to collapse into a single, ultra-massive object. This would be an incredibly rare and finely tuned scenario, but not entirely outside the realm of physics, especially in an environment as extreme as the Tarantula Nebula. There's also the possibility that a 136A1 formed through a combination of all these mechanisms: initial competitive accretion, followed by one or more mergers, all within a dense, turbulent environment that temporarily suppressed fragmentation. In such a chaotic cosmic cradle, nature might have found a way to sidestep the rules we assumed were unbreakable. Interestingly, computer simulations have begun to support some of these theories. Researchers have run complex models of star cluster formation in environments similar to the Tarantula Nebula, and these simulations sometimes produce runaway giants, stars that, through a combination of accretion and mergers, grow to hundreds of solar masses. But even these simulated monsters often require fine-tuned conditions and assumptions, suggesting that stars like our 136A1 are incredibly rare outcomes rather than regular features of cosmic evolution. Another factor to consider is metallicity, the abundance of elements heavier than helium in the star-forming gas. The Tarantula Nebula, located in the Large Magellanic Cloud, has relatively low metallicity compared to the Milky Way. This matters because high metallicity stars generate more radiation pressure due to higher opacities in their outer layers. In low metallicity environments, radiation escapes more easily, allowing stars to accrete more mass before radiation pressure becomes a limiting factor. This might help explain why a star like our 136A1 was able to form in the LMC and not in our own galaxy. Ultimately, our 136A1 may be the product of a cosmic perfect storm, where environmental conditions, cluster dynamics, metallicity, and gravitational chaos all align just right to allow a single object to break the rules. It may not be a reproducible process, which is why we don't see stars like this scattered across the sky. They are rare. They are exceptional. And they are reminders that the universe is not limited by our equations, it often writes new ones. The deeper we look into how our 136A1 formed, the clearer it becomes that our understanding of stellar birth is still incomplete. Stars are not merely objects, they are the results of fierce, dynamic processes governed by the intricate laws of physics, and sometimes, they find loopholes we didn't know existed. Our 136A1 stands as a beacon of that cosmic ingenuity, forged in fire, gravity, and perhaps a few stellar collisions. The very existence of our 136A1 is a cosmic defiance of what we thought we knew about the limits of star formation. For decades, astronomers have debated how big a star could actually get before the laws of physics push back. In textbooks and simulations alike, the commonly accepted upper limit for a star's mass has hovered around 100 to 150 times the mass of our Sun. This isn't an arbitrary number, it's based on models of stellar equilibrium, thermodynamics, and radiation pressure. But when a 136A1 burst onto the astronomical scene, it didn't just tiptoe past that limit, it smashed it, weighing in at an estimated 215 solar masses. The implications of this are staggering, because it means there's a massive loophole in our understanding of stellar genesis. To grasp why this is such a big deal, we have to dive into the concept of radiation pressure again. In the core of a massive star, fusion reactions release tremendous amounts of energy, creating light that exerts an outward force. The more massive the star, the more intense its radiation becomes. At a certain point, the radiation pressure becomes strong enough to counteract gravity itself, effectively halting any additional mass from accumulating onto the star. This theoretical point is called the Eddington limit, and it's one of the foundational constraints in stellar physics. According to these limits, stars more massive than about 150 solar masses should be inherently unstable. Either they blow off their excess mass through stellar winds, or they break apart entirely during formation. But our 136A1 doesn't care about the Eddington limit. It's not only stable, it's thriving, shining millions of times brighter than our Sun and burning with a ferocity that should have long ago torn it apart. How is this possible? One explanation lies in the chaotic environments of superstar clusters. When hundreds of massive stars are forming in the same compact region, as they do in the R136 cluster, the conditions become extreme enough that traditional star formation models, usually based on more isolated and tranquil environments, simply don't apply. These dense stellar nurseries are governed by turbulence, magnetic fields, shock waves, and gravitational interactions far more intense than anything we see in the quieter outskirts of our own galaxy. In such an environment, radiation pressure may be temporarily overwhelmed by sheer gravitational collapse or dynamically altered by complex feedback mechanisms that allow stars to grow much larger than expected. Another potential workaround for the Eddington limit involves anisotropic radiation, or uneven radiation flow. Our models often assume stars emit energy uniformly in all directions, but in reality, stellar radiation can be channeled in ways that allow material to continue falling in along the star's equator while excess radiation escapes along the poles. This breaks the symmetry assumed in simplified models and could allow a star to accumulate more mass before the outward radiation halts the process. Additionally, the opacity of the gas in the forming region plays a critical role. In regions with lower metallicity, like the Large Magellanic Cloud, the gas and dust are less sticky to radiation. This means photons can escape more easily, reducing radiation pressure and allowing gas to collapse more readily. That's a subtle, but crucial, difference that could mean the difference between a star capping out at 150 solar masses and one racing ahead to 200 or more. This lower opacity could act as a pressure release valve, giving stars like our 136A1 the room to grow without immediately triggering mass ejection. Even more radical ideas have been proposed to explain stars that challenge these limits. Some astrophysicists suggest that stellar collisions, already suspected in our 136A1's formation, might not just build massive stars but actually allow for the continued existence of ultra-massive objects well beyond conventional thresholds. When two massive stars merge, the resulting object inherits both the mass and momentum of its progenitors. But if this occurs early enough in their evolution, the new star can remain stable, at least for a time. It's a dangerous balancing act. One wrong step and the star could detonate or collapse, but under the right conditions, it might just work. Then there's the possibility that our equations need rewriting. The physics that govern stars are rooted in general relativity, nuclear fusion dynamics, and thermodynamics. These systems are immensely complex, and even small adjustments in our understanding of opacities, convection, or magnetic field interactions could open the door to much larger stellar masses. For example, some newer simulations incorporate rotational support, the idea that a rapidly spinning protostar can use angular momentum to counteract some of the effects of radiation pressure, delaying or even preventing mass loss. If our 136A1 is rotating rapidly, and we have reasons to believe it might be, this could be yet another factor helping it cheat the limits. The implications of this are profound. If one star like our 136A1 can form and survive well beyond the predicted mass limit, how many others have done the same without our knowledge? Are we underestimating the maximum potential of star formation across the cosmos? Could some of the early stars in the universe, population 3 stars, have been even larger, burning fast and bright in the primordial dark, seeding galaxies with heavy elements before collapsing into black holes? And speaking of black holes, the formation of a star as massive as our 136A1 is closely tied to the birth of black holes on the upper mass scale. If stars can form well above 200 solar masses, then perhaps they're the progenitors of intermediate mass black holes, a mysterious class that bridges the gap between stellar mass and supermassive black holes. Finding more stars like our 136A1 could help explain how some black holes in the early universe got so big, so fast. In many ways, our 136A1 is not just a star, it's a challenge to our cosmic rulebook. It forces astronomers to go back and question assumptions that once seemed airtight. The idea that stars shouldn't get this big now seems like an invitation to explore further rather than a hard stop. The universe has always found ways to surprise us, and our 136A1 is one of its most spectacular curveballs, a massive, brilliant outlier that hints at a deeper and perhaps stranger set of laws governing the formation of the stars themselves. In the vast, enigmatic theater of the cosmos, certain celestial objects stand out not just because of their scale or luminosity, but because they defy the very frameworks we use to understand the universe. Our 136A1 is one such object, a star so massive, so luminous, and so extreme in every measurable way that it doesn't just strain our scientific models, it threatens to unravel them. As we peer into its searing heart and measure its colossal proportions, we're forced to ask a profound question: is our 136A1 breaking physics? To be clear, this isn't just hyperbole. Our 136A1 isn't merely an edge case. It is an outlier so severe that it has triggered a re-evaluation of key tenets in stellar astrophysics. When scientists say our 136A1 might be breaking physics, they don't mean it's violating the fundamental laws of the universe like gravity or thermodynamics. Instead, what they mean is that our current physical models of how stars are born, evolve, and I don't comfortably account for something like our 136A1. It's not just a glitch in the system, it's a star that appears to exist outside the system's expected boundaries. Let's start with the very notion of star formation. According to decades of theoretical work and computer simulations, stars are formed when clouds of gas collapse under their own gravity. But once that mass crosses a certain threshold, radiation pressure becomes a problem. The star, trying to ignite nuclear fusion at its core, begins emitting light so powerfully that it pushes back on the incoming matter, stopping further accretion. This is the Eddington limit, and it's supposed to represent a ceiling for how big stars can grow. Our 136A1, however, blew past that ceiling. Its estimated mass of over 215 times that of the Sun suggests that either the Eddington limit is wrong or that something allows the star to bypass it. This is a big deal, because the Eddington limit isn't a minor side equation, it's one of the pillars of high-mass stellar theory. Violating it doesn't just affect models of star formation, it undermines our understanding of the life cycle of stars, the balance of forces in stellar atmospheres, and even the ways galaxies evolve. But the star's mass isn't the only problem. Its incredible luminosity, which is several million times that of the Sun, also stretches our models thin. According to our current equations, a star with that much radiation output should be shedding mass at a furious rate, so much so that it would rapidly fall back into the normal range of stellar masses. But our 136A1 appears to be stable. It exists in a sort of astrophysical twilight zone, massive enough to bend the rules, yet somehow avoiding the chaos those rules were designed to prevent. There are also questions about how stable our 136A1 truly is. Some models suggest that stars this massive should experience violent pulsations or even begin shedding their outer layers through enormous stellar winds, in a process called LBV, luminous blue variable instability. And yet, our 136A1 hasn't exploded or collapsed, and its surface, while turbulent, doesn't seem to match the runaway behaviors predicted in simulations. Could it be that our models are simply not equipped to handle such objects? Or are there additional forces at play, perhaps magnetic fields, angular momentum, or even unknown physical mechanisms, that are stabilizing this stellar behemoth? This line of thinking leads us to even deeper waters, because our 136A1 might not just be bending known physics, it might be pointing us toward new physics. Could the equations we use to describe stellar mass loss, opacity, or energy transport be incomplete at the highest mass scales? Are there unknown variables that only come into play in the extreme conditions near our 136A1's core? Some researchers have speculated that stars like our 136A1 could be governed by exotic matter interactions that we don't yet fully understand. At the immense temperatures and pressures in its core, conditions that far exceed anything we can replicate on Earth, could particles behave differently? Could quantum gravity effects start to make themselves known? While this is speculative, the truth is that we don't know, because no laboratory on Earth can produce a miniature version of our 136A1 to test our theories. In a very real sense, the star itself is the laboratory. Even the question of how our 136A1 will die pushes the limits of known physics. At its size, apparent stability supernova, a rare and violent explosion that leaves behind no remnant at all, is a real possibility. But that process only occurs within a very narrow band of masses and conditions. If our 136A1 exceeds that, it could collapse directly into a black hole, potentially of intermediate mass, something that remains one of the biggest unsolved mysteries in modern astrophysics. We've observed stellar mass black holes and supermassive ones, but the bridge between them, the so-called intermediate mass black holes, remains elusive. Our 136A1 might just be the missing link. Then there's the cosmic context. Our 136A1 resides in the Large Magellanic Cloud, a satellite galaxy of the Milky Way with lower metallicity than our own. Metals, in astronomical terms, refer to elements heavier than hydrogen and helium, and their presence affects how stars form and evolve. Lower metallicity allows gas to cool more efficiently, and reduces radiation pressure, which in turn can enable the formation of more massive stars. So in some sense, our 136A1 could be a product of its environment. But that just raises more questions. If such conditions allow these ultra-massive stars to exist, could the early universe, with its almost pure hydrogen-helium composition, have been teeming with them? And if so, what implications does that have for cosmic evolution, black hole formation, and the spread of heavy elements? The point is, every aspect of our 136A1, from its size and brightness to its origin and potential demise, pushes at the boundaries of what we consider settled science. It's not that we're throwing out the physics books entirely, but rather that we're realizing how much of them may need rewriting when it comes to the most extreme conditions in the universe. Our 136A1 is more than just a star. It's a cosmic riddle, a challenge from the universe to go deeper, think harder, and imagine beyond the constraints we once took as absolute. As telescopes improve and our models become more refined, we may begin to decode this mystery. Or perhaps we'll find that our 136A1 is merely the tip of the iceberg, a sign that the cosmos holds far more surprises than we ever dared believe. Observing a star like our 136A1 is no simple task. Unlike stars in our local stellar neighborhood, this one resides an astonishing 160,000 light-years away, buried deep within one of the most active and complex star-forming regions in the nearby universe, the Tarantula Nebula. But even distance isn't the biggest hurdle. The real challenge lies in the fact that our 136A1 does not exist in isolation. It is nestled inside the densely populated R136 star cluster, surrounded by dozens of other blazing stellar giants. Their proximity, both physically and visually from Earth, makes resolving individual stars in that region a monumental challenge, one that has tested the very limits of astronomical instrumentation. Enter the Hubble Space Telescope. Since its deployment in 1990, Hubble has become one of the most crucial tools in high-resolution astronomy, capable of seeing deep into crowded fields with a clarity unmatched by Earth-bound instruments, at least until very recently. In the case of our 136A1, Hubble was instrumental in separating its light from that of its close stellar neighbors. Prior to Hubble's observations, what we thought was a single super-bright star in the center of the R136 cluster turned out, upon closer inspection, to be a dense concentration of individual stars. But even then, picking apart the light from these massive objects was a task that pushed the telescope's optics to the limit. Using Hubble's Wide Field and Planetary Camera 2, WFPC-2, and later its Advanced Camera for Surveys, ACS, and Wide Field Camera 3, WFC-3, astronomers managed to obtain multi-wavelength images of the Tarantula Nebula with incredible detail. These instruments enabled observations in ultraviolet, optical, and near-infrared light, each wavelength revealing different properties of the region. Ultraviolet imaging, in particular, allowed scientists to isolate the extremely hot, young, and massive stars like our 136A1, that are heavily emitting in that part of the spectrum. By breaking the light from these stars into their component wavelengths, analyzing their spectra, astronomers could determine key characteristics such as surface temperature, composition, wind velocities, and mass loss rates. Spectroscopy is vital because it allows scientists to decode what elements are present in the star's atmosphere and how fast material is moving away from its surface, giving clues to the mass and evolutionary stage of the star. In our 136A1's case, this revealed the signs of intense stellar winds, which are a hallmark of extremely massive stars and contribute to their ongoing mass loss. But even Hubble has its limitations. Its resolution, while extraordinary for a space-based instrument, still can't always perfectly resolve stars that are packed together as tightly as those in our 136. This is where the Very Large Telescope, VLT, a ground-based facility operated by the European Southern Observatory in Chile, enters the picture. The VLT consists of 4 individual optical telescopes, each with an 8.2-meter diameter primary mirror, working either independently or together through interferometry. While Earth's atmosphere normally limits the clarity of ground-based telescopes due to atmospheric turbulence, the twinkling effect we see with our eyes, the VLT uses a technique called adaptive optics. This system corrects for atmospheric distortion in real time, allowing the telescope to achieve near Hubble-level resolution, or even surpass it in some infrared observations. In 2010, Astronomers using the VLT Symphony instrument, spectrograph for integral field observations in the near-infrared, delivered the most detailed observations of our 136A1 to date. They managed to resolve our 136A1 clearly enough to measure its mass, placing it between 215 and 265 solar masses, more than double what had previously been thought possible for a star. This was a watershed moment in stellar astrophysics. Suddenly, we had direct observational evidence that stars could grow to masses far exceeding previous theoretical limits. The VLT observations also provided updated estimates of our 136A1's temperature and luminosity, and revealed that it was blowing off material in colossal stellar winds traveling at over 2,000 kilometers per second. These winds are not gentle breezes. They're more like a continuous explosion. The star is actively losing mass every second, casting off vast quantities of material into its environment, which in turn helps enrich the interstellar medium with heavier elements like carbon, nitrogen, and oxygen. One of the most exciting aspects of observing our 136A1 is that it is still relatively young. This means we are catching it during its most active and luminous phase, possibly only 1 million or 2 years into its life. For astronomers, this is like observing a firework just after it's launched, right at its most dazzling and intense phase. Such timing is invaluable for understanding the life cycle of the universe's most massive stars. But Hubble and the VLT are not the end of the story. As we step into a new era of astronomy, new instruments are coming online that will likely offer even greater insight into our 136A1. The James Webb Space Telescope, JWST, with its unparalleled infrared capabilities and extreme sensitivity, is expected to pierce deeper into dusty star-forming regions like the Tarantula Nebula than ever before. While JWST was designed more for deep-time cosmic archaeology than nearby massive stars, its high-resolution instruments could still contribute to follow-up observations, especially in the infrared, where cooler components of the star-forming region, and possibly its early formation history, can be observed. Meanwhile, the extremely large telescope, ELT, currently under construction by the European Southern Observatory, is set to dwarf all existing optical telescopes. With a primary mirror 39 meters in diameter and equipped with next-generation adaptive optics, the ELT promises to deliver resolution and sensitivity that will revolutionize our understanding of stars like our 136A1. It may finally allow astronomers to definitively answer whether our 136A1 is a single star or a tightly bound system of multiple massive stars. If it's one object, then the laws of star formation may need rewriting. If it's several, then we've learned something else entirely about stellar clustering and gravitational dynamics. Observing our 136A1 is more than an exercise in technological prowess. It's a confrontation with the unknown. It forces astronomers to design better instruments, refine their theories, and invent new techniques to understand what they're seeing. Every photon we collect from this distant colossus is a whisper from a frontier of physics we have only begun to explore. Our 136A1, therefore, doesn't just test the limits of our telescopes, it stretches the limits of our imagination. And in that pursuit, every new observation becomes not just a snapshot of the star itself, but a mirror reflecting the growth of human understanding. The staggering distance between us and our 136A1 cannot be overstated. Located approximately 160,000 light-years from Earth, this colossal star resides far outside our Milky Way galaxy, tucked away in a satellite galaxy known as the Large Magellanic Cloud. To comprehend this distance, one must break free from the familiar earthly measurements of kilometers or miles and instead embrace the sheer immensity of intergalactic space, distances so vast that the fastest thing in the universe, light itself, takes 160 millennia to make the journey from our 136A1 to our telescopes. A light year, the distance light travels in 1 Earth year, is about 9.46 trillion kilometers, 5.88 trillion miles. Multiply that by 160,000 and you begin to approach the scale of separation between Earth and this cosmic Goliath. That equates to over 1.5 quintillion kilometers, a number so enormous that it loses all meaning without a proper cosmic perspective. Let's try anchoring this against other known celestial distances. The closest star to Earth after the Sun is Proxima Centauri, which lies just over 4.2 light-years away. Our entire solar system, from the Sun to the outer edge of the Oort cloud, is a few light days across at most. Even the center of our own Milky Way galaxy is about 26,000 light-years from us, still less than 1/5 the distance to our 136A1. So when we say this star is 160,000 light-years away, we're not just talking about a long road trip across the galaxy. We're talking about stepping beyond our galactic borders, into a neighboring realm altogether. The Large Magellanic Cloud, LMC, the galaxy that hosts our 136A1, orbits the Milky Way and is considered a dwarf irregular galaxy. Though it is smaller than the Milky Way, it is one of the most luminous galaxies in the local group and a prolific star factory. Its relative proximity, on the galactic scale, makes it a prime target for studying phenomena that are too rare or obscured within the Milky Way itself. And yet, despite being a neighbor in cosmic terms, the LMC is still so far that if it were possible to travel at the speed of NASA's Voyager 1, currently moving at about 17 kilometers per second, it would take more than 2.8 billion years to reach our 136A1. One of the extraordinary things about such distance is how long the information we're seeing has been in transit. The light that reaches our telescopes today left our 136A1 before humans had invented writing, before civilization as we know it existed, and long before the Earth bore any trace of the modern world. When we observe this star, we are seeing it not as it is today, but as it was during the time of early Homo sapiens, when mammoths roamed and Earth's geography was still reshaping. That delay in light transmission transforms our telescopes into time machines. Peering into the Large Magellanic Cloud isn't just a geographical exercise, it's a look into a distant past. We do not know what our 136A1 looks like now in real time. Has it changed dramatically since that light left? Is it still burning as ferociously as it was 160,000 years ago? Or has it already met its explosive end in a brilliant supernova, a spectacle that has yet to reach us because of the travel time involved? These are open questions, underscoring the surreal nature of deep space astronomy. What's more, our 136A1's distance makes it a critical piece of the cosmic ladder, the sequence of methods astronomers use to measure the scale of the universe. By studying stars in nearby galaxies like the LMC, scientists calibrate the relationships between a star's brightness, color, and distance, which can then be applied to more distant galaxies. Our 136A1, as one of the brightest and most massive stars ever observed, plays a small but important role in helping astronomers establish how far away other objects in the universe might be. But its remoteness also introduces observational challenges. At that distance, even the most sophisticated telescopes can struggle to isolate it from its stellar neighbors. Distinguishing one point of light from another in a star cluster so dense, so far away, and filled with other similarly massive stars requires exceptional instruments, precise targeting, and a deep understanding of how light behaves across vast stretches of space. Still, despite all of these limitations, astronomers have managed to piece together a surprisingly detailed picture of our 136A1. They've measured its mass, temperature, luminosity, and even theorized its future, all based on photons that began their journey when human culture was still in its infancy. It's a humbling thought that a single star, far beyond our galaxy, can be studied so thoroughly even though it's separated from us by both distance and time. In some ways, the vast distance that separates us from our 136A1 adds to its mystique. It feels untouchable, otherworldly, something so powerful, so rare, and so luminous, yet so remote that it exists more like a myth carved into the fabric of space. And yet it is real. The photons it emits cross a cosmic ocean to reach us, whispering secrets of a universe still full of wonder and strangeness. Could a star like our 136A1 exist in the Milky Way? It's a question that probes the very foundations of stellar formation and galactic environment. And the short answer is, while not entirely impossible, it's highly unlikely. To understand why, we have to look at what it takes to create a star like our 136A1, and then examine whether our own galaxy can provide the necessary conditions. The formation of our 136A1 is an extreme event that requires a very specific kind of stellar nursery, a region of immense gas density, low metallicity, strong turbulence, and rapid, efficient collapse of massive clouds of hydrogen. Such conditions are not evenly spread across all galaxies. While the Milky Way has many massive stars, some weighing in at 50 or even 100 times the mass of the Sun, it doesn't seem to produce stars quite at the scale of our 136A1, which exceeds 200 solar masses. One of the biggest reasons for this may come down to metallicity, or the proportion of elements heavier than helium in a star-forming region. In the Milky Way, star-forming clouds have relatively high metallicity because the galaxy has been through billions of years of stellar evolution, where each generation of stars seeds the next with heavier elements through supernova explosions. Higher metallicity tends to increase radiation pressure in young stars, which disrupts their accretion process, the gathering of mass during formation. This extra pressure often prevents a young protostar from gaining as much mass as it might in a lower metallicity environment. By contrast, the Large Magellanic Cloud, home of our 136A1, has lower metallicity, more akin to conditions in the early universe. Lower metallicity means less radiation pressure during star formation, allowing protostars to accumulate much more mass before the process is halted by stellar winds or feedback. In essence, the LMC has the right, primordial, conditions that may be closer to those that existed when the first stars, the population 3 stars, formed shortly after the Big Bang. These conditions are more favorable for creating supermassive stars. Another factor is gas density and cluster dynamics. The cluster R136 is not just home to our 136A1, it's bursting with other massive stars as well. This environment suggests that the region experienced an unusually high-efficiency starburst, collapsing large amounts of gas in a relatively short period. Such events are relatively rare even on cosmic timescales. While the Milky Way does have dense clusters, such as the Arches cluster and the quintuplet cluster near the galactic center, none of them seem to match the mass-rich density and extreme youth of our 136. These clusters harbor stars up to maybe 100 to 150 solar masses, but even that is pushing the upper edge of what's commonly observed in our galaxy. Then there's the issue of stellar feedback. Massive stars are extremely disruptive. They blast out intense radiation, stellar winds, and eventually supernovae that blow away surrounding gas. In the Milky Way, the feedback mechanisms in most regions seem to limit how big a single star can grow by disrupting star formation early. In the more chaotic, irregular, and perhaps less self-regulated environment of the Large Magellanic Cloud, the formation of such a monster might sneak past these usual checks and balances. There's also a spatial dynamic to consider. The Milky Way's spiral arms are spread out in a disk about 100,000 light-years across. Its interstellar medium is filled with regions of various temperatures, densities, and star-forming activity, but most of it is not in the extreme regime required to birth something like our 136A1. On the other hand, the LMC, though smaller, has particular regions like the Tarantula Nebula where everything aligns just right: gas supply, gravitational collapse, environmental instability, and low metallicity, to create a stellar behemoth. It's worth noting that some stars in our galaxy have, at times, been mistaken for ultramassive stars, only for further analysis to reveal they were either binaries or slightly overestimated in their mass. One example is Eta Carinae, a famous massive star system in the Carina Nebula. At one point, it was considered to be among the most massive stars known, with estimates ranging up to 150 solar masses. But it later turned out to be a binary system, and the most massive component is likely under 100 solar masses. Even so, Eta Carinae is wildly unstable, with massive eruptions and intense mass loss, highlighting the fragility of massive stars in our galaxy. This leads to an important point. Perhaps it's not that the Milky Way can't make stars like our 136A1, but that it doesn't often allow them to survive or remain observable for long. If a 200-plus solar mass star did form here, it might quickly blow itself apart, shed a massive fraction of its outer layers, or go supernova before we ever had a chance to study it in detail. It could be a fleeting flame that's difficult to catch in the act. Or it may be buried so deep in dust that it remains obscured from view even by our most advanced telescopes. The future may change this understanding. With next-generation instruments like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, astronomers may uncover previously hidden massive stars within our own galaxy or its halo. These tools will allow us to peer deeper into dense and dusty regions that were previously opaque to observation, possibly revealing candidates for the next R136A1-like object, if they exist here at all. Until then, R136A1 remains an exotic outlier, a stellar titan forged in a neighboring galaxy under exceptional conditions. It stands as a reminder that the universe is not uniformly governed by our expectations or local norms. While the Milky Way has its own impressive roster of stars, it may simply lack the specific environmental cocktail needed to birth a giant like R136A1. Or perhaps, like so many cosmic secrets, it's still hiding in plain sight, just waiting for the right eyes to find it. The life of R136A1 is already one of extremes: extreme heat, mass, luminosity, and scale, but its death promises to be even more spectacular. When stars like our Sun reach the end of their lives, they tend to go out quietly, shedding their outer layers and leaving behind a white dwarf. But a star like R136A1 doesn't have that luxury. It was born for violence, and its end will almost certainly shake the very fabric of space-time. The question isn't whether it will explode, it's how. One possibility that has long captured the imagination of astrophysicists is the core collapse supernova, a titanic explosion that occurs when the fusion reactions in a star's core can no longer resist the crushing force of gravity. In a typical massive star, once iron builds up in the core, fusion halts. Iron doesn't yield energy through fusion like lighter elements. Gravity wins, the core collapses, and the outer layers rebound and explode outward in a spectacular supernova. For a star as massive as R136A1, this would be no ordinary supernova. It would be a hypernova, a term used to describe the most energetic type of core collapse supernova, potentially releasing over 100 times more energy than a standard one. But even a hypernova might not be the most dramatic ending available to R136A1. Given its extreme mass, it might instead undergo what's known as a parent stability supernova. This is an incredibly rare and violent process predicted for very massive stars with low metallicity, conditions that R136A1 seems to meet. In such stars, the core becomes so hot that gamma-ray photons, instead of supporting the core with radiation pressure, begin spontaneously converting into matter, specifically, pairs of electrons and positrons. This unexpected drop in radiation pressure causes the core to collapse and ignite runaway oxygen fusion. The result is an explosion so powerful that it doesn't just tear the outer layers off the star, it completely unmakes the star, leaving no remnant behind. No neutron star, no black hole. Just a vast shell of high-energy debris hurled into space. This outcome would be stunning in its finality. It would be as if a cosmic giant simply vanished, its mass dispersed into the cosmos to enrich future generations of stars with the heaviest elements. But whether R136A1 will take this path depends on many delicate physical factors, especially its mass at the time of death. As the star sheds material through strong stellar winds, something massive stars do prodigiously, it may reduce its mass enough over time to fall below the threshold for parent stability, making the hypernova or black hole path more likely. Which brings us to the most captivating possibility, the formation of a black hole. If the core of R136A1 retains enough mass at the end of its life, the collapse may be so complete that not even the rebound shock wave of a supernova can escape. Instead, the core shrinks into a singularity, a point of infinite density surrounded by an event horizon from which nothing, not even light, can return. This would mark the birth of a stellar mass black hole, possibly one of the most massive ever formed through stellar collapse. Some estimates suggest that if R136A1 retains more than 100 solar masses at the moment of death, the resulting black hole could be well over 50 to 80 solar masses, a behemoth by stellar standards. But there's another twist in this cosmic death spiral: gamma-ray bursts, GRBs. These are among the most energetic explosions in the universe, releasing more energy in a few seconds than the Sun will in its entire 10 billion year lifetime. GRBs are thought to be linked to the collapse of massive stars into black holes, specifically, when a rapidly rotating core forms a spinning black hole and launches twin jets of radiation along its rotational poles. If Earth happened to lie in the path of one of these jets, the burst could be visible across vast distances. Some have speculated that a close-range gamma-ray burst could even sterilize planets in its beam. Thankfully, at 160,000 light-years away, our 136A1 poses no such threat to us, but the burst would be an astonishing event for astronomers to witness. All these possibilities hinge on one key uncertainty: how much mass our 136A1 will lose before it dies. Massive stars like this one don't sit still, they rage and boil, casting off outer layers through powerful stellar winds, particularly if they are wolf-rayet stars, as our 136A1 is classified. These winds can peel off dozens of solar masses over time. If our 136A1 sheds enough material, it may never reach the conditions required for parent stability, and might instead follow the more normal path of core collapse. But if it retains enough mass, it may become one of the very few stars to undergo complete annihilation through parent stability. It's also worth considering that the death of our 136A1 might not be an isolated event. Situated in the densely packed R136 cluster, the star may affect, or be affected by, the fates of nearby massive stars. Their deaths may trigger shockwaves that compress nearby gas, igniting further star formation, or even accelerating the demise of their neighbors through gravitational interactions. It's not just one death, it's a chain reaction of stellar violence. One final mystery looms: has our 136A1 already died? Because it's 160,000 light-years away, we are seeing the star as it was 160,000 years ago. It's possible, though not certain, that in real time, our 136A1 has already exploded. Its light just hasn't reached us yet. If and when it does, we may observe one of the most cataclysmic events in modern astronomy: a supernova, a GRB, or perhaps an eerie silence followed by gravitational waves heralding the silent birth of a black hole. In any case, the end of our 136A1 will not be a whimper. It will be a roar across the void, echoing in radiation, neutrinos, and gravity, marking the conclusion of one of the most colossal lives ever recorded in the cosmos. Our 136A1 is not just a star, it is a laboratory, a natural experiment conducted in the far reaches of the universe, challenging our models, forcing us to redraw our charts, and compelling scientists to confront the outermost limits of stellar possibility. Its existence stretches the rules of stellar formation and evolution in ways that make it a central focus in modern astrophysics. This isn't simply a big, bright object, it's a fundamental anomaly, a stellar outlier that behaves like a cosmic mirror, reflecting both what we know and what we still don't understand about the physics of stars. What makes our 136A1 so compelling to scientists is that it breaks thresholds we thought were impassable. Before its discovery, many theorists believed that stars couldn't form with initial masses exceeding about 150 times the mass of the Sun. This limit, based on the balance between gravitational collapse and the outward pressure of radiation, seemed a hard boundary. Too much mass, and the star's own light would push the inflowing gas away before it could accumulate. But our 136A1 shattered that barrier. Its estimated initial mass was somewhere around 250 to 300 solar masses, depending on the model. That's not a minor overshoot. That's a leap over what many thought was a physical impossibility. This alone makes it a touchstone for studying the mechanisms of stellar birth. How could a star gather that much material without blowing itself apart during formation? What role did its environment, inside the R136 cluster, deep within the dense Tarantula Nebula, play in nurturing such extreme growth? Could unusually low metallicity in the Large Magellanic Cloud have facilitated the conditions for a supermassive star to form by reducing radiation-driven mass loss? These are not idle curiosities. They're questions that go to the heart of how matter coalesces into light-bearing structures across the cosmos. And then there's its evolutionary path. Because of its incredible mass and luminosity, our 136A1's lifetime is compressed into just a few million years, an eye blink on cosmic scales. It evolves at hyperspeed, burning through its hydrogen core at a ferocious rate, shedding layers of mass through intense stellar winds, and progressing rapidly toward a spectacular end. This speed offers a unique opportunity. By observing it now and comparing it to slightly younger or older massive stars in the same cluster, astronomers can construct a living timeline of stellar evolution, watching the life of a supermassive star unfold almost in real time, albeit over millennia. Even its composition is fascinating. Our 136A1 belongs to the wolf-rayet category, a class of stars known for their stripped-down surfaces, fierce radiation, and strong stellar winds. These are the evolutionary successors to the most massive O-type stars, and they give us direct insight into the processes of mass loss, core heating, and fusion transitions. The fact that a 136A1 still retains much of its initial mass despite being in this stage suggests that wolf-rayet behavior in supermassive stars could be significantly different from what we observe in their smaller cousins. Understanding those differences could help explain a wide range of cosmic phenomena, from the dynamics of early galaxies to the chemical enrichment of interstellar space. The star also plays a vital role in refining our models of radiative transfer, convection, and magnetic field interactions within massive stars. Traditional stellar evolution codes were not designed to handle such extremes. Researchers have had to push their simulations into previously unexplored regimes, adjusting parameters, solving modified versions of the equations of hydrostatic equilibrium, and exploring feedback loops between radiation pressure, mass loss, and fusion rates. Every new insight drawn from our 136A1 leads to improvements in our predictive tools, which then get applied to a range of astrophysical systems, from starburst galaxies to the first generation of stars in the early universe. In fact, that last point might be one of the most profound. Our 136A1 may be the closest analog we have to population 3 stars, the first stars that ever formed in the universe. These primordial giants, forged in a cosmos devoid of metals, were thought to be incredibly massive, short-lived, and intensely luminous. Because they formed more than 13 billion years ago and have long since died out, we can't observe them directly. But a 136A1 may provide a proxy, a glimpse into the kind of conditions and outcomes that characterize those ancient stellar titans. By studying its life cycle, scientists can test hypotheses about the early universe, the reionization epoch, and the seeding of heavier elements across galaxies. The implications even extend into gravitational wave astronomy. If our 136A1 collapses into a massive black hole, it could become part of a binary system and eventually merge, sending ripples through space-time detectable by instruments like LIGO and Virgo. In fact, the discovery of surprisingly massive black holes and gravitational wave events has already forced scientists to reconsider their assumptions about black hole formation, and stars like our 136A1 might be the origin of those mysterious objects. Ultimately, what captivates scientists most about our 136A1 is that it doesn't sit comfortably within any existing framework. It dares us to stretch the definitions of stellar structure, to test our mathematical models, to revise our assumptions about how stars are born, live, and die. It sits on the edge of the possible, a bridge between the familiar world of standard stellar physics and the wild frontier of what stars can be under the most extreme conditions. Every photon it emits, every layer it sheds, every fraction of a second it survives, is data, a message from the cosmos challenging our understanding of what nature is capable of building. In that sense, our 136A1 isn't just fascinating, it's indispensable. It's the star that rewrites the textbooks, the anomaly that defines the rule, the glowing ember in the sky daring us to imagine something more massive, more luminous, more intense. It is the frontier of stellar science itself. The influence of our 136A1 extends far beyond its immediate surface. This is not a star that merely exists within its environment, it actively shapes it. A cosmic architect of sorts, our 136A1 commands its surroundings through blistering radiation, powerful stellar winds, and immense gravitational presence, transforming the fabric of space around it. To understand its full impact on nearby systems is to appreciate how a single massive star can alter the structure and evolution of an entire region of space. Stars like our 136A1 don't just emit light. They release torrents of high-energy radiation, especially in the ultraviolet spectrum. This radiation ionizes the hydrogen gas surrounding the star, stripping electrons from atoms and creating vast bubbles of ionized plasma. In the Tarantula Nebula, already one of the most energetic star-forming regions known, our 136A1 contributes a disproportionate share of the ultraviolet output, helping carve out massive cavities within the surrounding interstellar medium. This ionization front is not a passive feature, it's dynamic, pushing outward, compressing nearby clouds of gas, and potentially triggering the collapse of smaller clumps into new generations of stars. That process, known as radiative triggering, is one of the paradoxes of massive stars. On one hand, their immense radiation pressures can blow gas away, preventing star formation. On the other hand, in certain regions, that same pressure can compress clouds just enough to induce gravitational collapse, igniting stellar birth. So a 136A1, while destructive, could also be a catalyst for creation. It tears apart some structures while sculpting others into nurseries for future stars. The effect of our 136A1's radiation is compounded by its stellar winds. These winds are not gentle breezes. They are fierce outflows of charged particles accelerated to speeds of over 2,000 km per second. These outflows carry with them enormous amounts of momentum and energy, slamming into surrounding gas and dust with forceful pressure. Over time, this produces large-scale shocks in turbulent regions within the nebula, further disrupting or compressing matter. The resulting environment is one of intense feedback, a tug-of-war between destruction and creation, chaos and order. In the cluster R136, which hosts our 136A1, there are dozens of other massive stars, some nearly as extreme in mass and luminosity. But our 136A1 stands out even among these giants. Its radiation and winds dominate the collective feedback mechanisms, influencing the gas dynamics of the cluster on a scale unmatched by its siblings. This interaction among massive stars also creates stellar wind collisions, places where the outflows from different stars crash into one another, creating regions of even higher temperature and energy. These zones can emit X-rays, generate shock fronts, and even influence magnetic fields within the nebula. Such extreme conditions have a profound effect on the potential planetary systems that might one day form in the vicinity. While we often think of solar systems forming peacefully in cool, quiet clouds, the environment near our 136A1 is anything but tranquil. Any protoplanetary disk within several light-years would be bombarded by ionizing radiation and eroded by stellar winds, potentially stripping away gas before planets could even form. This hostile radiation would vaporize ices and destabilize dust structures, possibly preventing the development of gas giants and even rocky planets. So in a very real way, our 136A1 could prevent the birth of planetary systems near it, obliterating the raw materials needed for worlds like ours. Moreover, the radiation pressure from such a massive star doesn't just impact gas and dust, it also exerts influence on nearby stars themselves. Less massive stars in the vicinity may find their own winds and mass loss rates affected by the overall pressure balance in the cluster. Some may even experience gravitational perturbations if our 136A1 undergoes major mass ejections, redistributing mass and altering the local gravitational landscape. Although stellar dynamics in massive clusters are complex and multibody, a single supermassive star like our 136A1 can subtly, but significantly, affect the orbital characteristics and angular momentum of neighboring systems. Then there is the matter of metallicity enrichment. Stars like our 136A1 forge heavier elements in their cores, and when they lose mass through winds or eruptive outbursts, they seed the surrounding space with freshly minted carbon, oxygen, nitrogen, and other elements. This process of enrichment is crucial. It's how later generations of stars and planetary systems get the building blocks necessary for complex chemistry and life. Our 136A1, already shedding vast quantities of mass, may be enriching the Tarantula Nebula with materials that will one day find their way into new stars, new planets, and possibly even new biospheres. In this way, even though it might prevent life nearby now, it could help enable it in the distant future. This chemical seeding doesn't occur in isolation. It interacts with the nebular gas and complex, three-dimensional patterns that astronomers observe using high-resolution spectroscopy. The resulting data gives us insight into the kinematics of outflows, the evolution of dust grains in high-radiation environments, and the multi-phase structure of the interstellar medium. Our 136A1's influence acts like a probe, illuminating how energy and matter flow through dense star clusters and how feedback loops govern star formation across galaxies. And we cannot forget the eventual endgame. When our 136A1 does explode, whether as a hypernova, parent stability supernova, or direct black hole collapse, the energy released will dwarf even its current output. A supernova of that magnitude could ionize gas clouds many light-years away, sweep away entire dust lanes, and trigger a wave of secondary star formation far from its origin. It could also generate gamma-ray bursts or relativistic jets capable of sterilizing nearby systems or altering molecular structures in clouds poised on the edge of collapse. Even though it's located 160,000 light-years from Earth, the implications of such an event in a closer region would be dramatic. Any hypothetical life-bearing systems near our 136A1 wouldn't survive the final blast. Even more fascinating is the thought that such an explosion could leave behind an intermediate mass black hole, an object that itself might shape the future gravitational dynamics of the region, drawing in stars, disrupting orbits, and potentially feeding on gas and dust for millions of years. The complexity of these interactions is what makes our 136A1 such a compelling focus for multi-wavelength astronomy. Observations from optical telescopes, infrared detectors, ultraviolet arrays, X-ray observatories, and even radio telescopes all contribute to a complete picture of how this one star influences its neighborhood. It's a microcosm of stellar feedback, an energetic crucible where the interplay of light, matter, gravity, and time can be studied in exquisite detail. And from a theoretical perspective, this influence extends to cosmological models as well. When astronomers simulate galaxy formation and evolution, they include stellar feedback as a key ingredient. Massive stars like our 136A1 are the cornerstone of those models. Without them, galaxies would form too many stars too quickly. Their feedback regulates star formation, prevents runaway collapse, and maintains the delicate balance that leads to the spirals, ellipticals, and irregular galaxies we see in the universe today. In short, our 136A1 isn't just a local titan, it's a galactic sculptor. Its presence bends the structure of its environment in real time, its output travels for light years, its death will echo through its host cluster, and its legacy will stretch across stellar generations. For astronomers trying to understand how stars shape galaxies, how feedback controls star birth, and how energy gets distributed in the universe, our 136A1 is less a star and more a cornerstone. If our 136A1 were closer, significantly closer, to Earth, the consequences would be both terrifying and awe-inspiring. It's difficult to overstate the scale of its power, because even at its current distance of 160,000 light-years, this single star can be studied by astronomers with detailed precision. But imagine if instead of residing in the large Magellanic Cloud, our 136A1 were situated within our own Milky Way galaxy, perhaps even in our cosmic backyard. What would happen if this monster of a star were just tens or hundreds of light-years away, rather than thousands? To begin, let's consider a relatively safe distance, say about 100 light-years, still far enough that Earth wouldn't be instantly vaporized, but close enough that its effects would be felt profoundly. At this range, the sheer luminosity of our 136A1 would outshine every other star in the sky. Its brightness would dwarf that of Sirius, currently the brightest star visible from Earth, and would likely rival or surpass the full moon in intensity. Night would never truly be dark again. The skies over Earth would glow with a pale bluish-white light from this colossal furnace, visible even during the day under certain atmospheric conditions. Astronomers would no longer need powerful telescopes to study it. It would be a prominent, unavoidable feature of the night sky for all humanity. But brightness would be the least of our concerns. R136A1 emits extreme levels of ultraviolet UV radiation. Unlike visible light, UV radiation can be damaging to biological tissues. Even at a distance of 100 light-years, the level of incoming UV could be enough to start disrupting Earth's ozone layer, the protective shield that guards us from harmful solar and cosmic radiation. Without this natural defense, life on Earth would face a massive surge in genetic mutations and disruption of photosynthesis in plants and phytoplankton, the foundation of most food chains. Entire ecosystems could begin to unravel. And it doesn't stop with UV radiation. The powerful stellar winds from R136A1, composed of high-energy charged particles, would carry intense solar-like activity across interstellar space. While interstellar winds dissipate with distance and time, a star of this size and output could inject highly energized particles into our region of the galaxy. This particle flux could disturb Earth's magnetosphere, damage satellites, and interfere with electronic communications, effects similar to but far worse than geomagnetic storms caused by our own sun's coronal mass ejections. Now imagine a scenario where a 136A1 is not just 100 light-years away, but a mere 10 light-years distant, a frighteningly close proximity in cosmic terms. At this range, Earth would be in grave danger. The star's UV radiation and stellar winds would saturate the solar system, likely overwhelming our atmosphere's ability to protect us. The environment would become increasingly hostile to life, with accelerated climate disruption, direct biological damage, and rising levels of radiation at the surface. The interplanetary space environment would become far more energetic, increasing drag on satellites and exposing astronauts to deadly levels of cosmic radiation. Furthermore, the heliosphere, the sun's protective bubble of influence in the solar system, could become distorted or even penetrated by our 136A1's influence. This could drastically alter space weather conditions throughout the solar system, affecting not only Earth, but every planet and moon within it. Space travel would become infinitely more dangerous, and shielding technologies would need to evolve dramatically just to keep pace with the constant influx of high-energy radiation. Now let's push this speculative scenario even further. If our 136A1 were as close as Alpha Centauri, just 4.3 light-years away, it would dominate the sky with an intensity we can barely imagine. From Earth, it would appear as a blinding, bluish-white beacon in the heavens. The UV radiation would be so intense that no natural atmosphere could fully protect against it. Earth's biosphere, as we know it, would be under existential threat. Oceanic plankton might collapse from excessive radiation, the ozone layer would likely be obliterated, and direct exposure to sunlight could be lethal. Civilization would be forced underground or behind protective domes. Life on the surface would either be extinct or heavily mutated. But the most catastrophic scenario comes not from the star's presence, but from its demise. If our 136A1 were this close and entered its final stage of life, exploding as a supernova or hypernova, the results would be apocalyptic. A hypernova could release as much energy in a matter of seconds as our Sun will over its entire 10 billion-year lifetime. The resulting gamma-ray burst, if directed even remotely toward Earth, would sterilize the planet. It would destroy the ozone layer almost instantly, causing intense ultraviolet radiation from our own Sun to flood the surface. This alone would be enough to collapse entire ecosystems within days or weeks. And if the gamma-ray burst was perfectly aligned with Earth, the outcome would be even more immediate. Gamma rays are invisible, high-energy photons capable of ripping apart molecular bonds. A direct hit would bombard the upper atmosphere with energy, initiating a chain reaction of chemical changes that could block out sunlight, poison the air, and trigger a global cooling event or even an extinction-level winter. Historically, some scientists have speculated that gamma-ray bursts from unknown past supernovae may have caused ancient extinction events on Earth. Our 136A1, if located nearby, would be a ticking time bomb capable of such devastation. There's also the possibility of the formation of a black hole. If our 136A1 ended its life in a direct collapse, forming a black hole without a visible supernova, its gravitational pull wouldn't magically suck everything in, but it could begin affecting the orbits of nearby stars and solar systems. At a very close range, gravitational interactions could destabilize entire systems, potentially slinging planets from their orbits or drawing them in over time. The direct impact on Earth would depend on proximity and vector, but in a tightly packed galactic neighborhood, the formation of a nearby black hole would be a dramatic, disruptive event. Thankfully, in reality, stars as massive as our 136A1 do not and cannot form in our solar neighborhood. The region near our Sun is relatively calm, a cosmic suburb far removed from the violent stellar nurseries found in starburst galaxies or dense clusters like our 136. The Milky Way has many large stars, but nothing quite like our 136A1 anywhere near us. The largest and most luminous stars tend to form in very specific environments, dense molecular clouds where gravity and turbulence interact in chaotic yet productive ways. These environments simply don't exist in the same way near our solar system. Still, this thought experiment serves as a chilling reminder of the fragility of life in the universe. While the cosmos is vast, and most of it seems empty and quiet, there are engines of such violence and power that, if placed closer to us, would unravel everything we know in a matter of moments. Our 136A1 is a distant monster, but one that reveals just how dangerous the universe can be, and how lucky we are that such titans lie far away. As we stand at the brink of a new era in observational astronomy, the future of studying massive stars like our 136A1 is set to expand in ways that were unimaginable just a few decades ago. Our 136A1, with its incredible size, brightness, and extreme physical characteristics, has already provided an immense challenge to existing models of stellar physics. Yet, the real revolution in our understanding of this cosmic monster, and others like it, is just beginning, thanks to the advent of next-generation telescopes such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT. These instruments represent the cutting edge of human capability, promising to peel back the layers of mystery that still enshroud the universe's most massive stars. The JWST, launched successfully in late 2021 and now fully operational, is designed to observe the universe in infrared wavelengths. This is especially important for studying massive stars like our 136A1 for several reasons. Firstly, our 136A1 resides in the Tarantula Nebula, a region of intense star formation and swirling interstellar dust. Dust, while a key ingredient in star formation, also obscures visible light, making it difficult to observe the internal structure and dynamics of star-forming regions with conventional optical telescopes. Infrared light, however, can penetrate this dust, allowing JWST to provide high-resolution views of the environments that give rise to stellar giants like our 136A1. By focusing on infrared wavelengths, JWST can do more than just see through the dust. It can directly observe the early stages of massive star formation. One of the biggest unanswered questions about stars like our 136A1 is, how do they form? Current models suggest that stars shouldn't be able to accrete material beyond about 150 solar masses, yet our 136A1 somehow did. JWST's sensitivity to faint heat signatures and early stellar emissions means it could detect protostars in the act of forming, offering clues about whether our 136A1-like stars are born from the collapse of single, massive gas clouds, or through the merger of smaller stars. Understanding this process could reshape our entire theory of stellar evolution. Moreover, JWST's suite of powerful instruments, such as the near-infrared spectrograph, NIR-SPEC, and mid-infrared instrument, MIRI, will allow scientists to analyze the chemical composition, temperature, and density of the gases surrounding our 136A1. These readings will shed light on the interactions between our 136A1 and its environment, how it shapes nearby star formation through stellar winds and radiation, and how feedback from such a luminous object influences the evolution of its surrounding cluster. Then there's the Extremely Large Telescope, ELT, currently under construction in the Atacama Desert of Chile. Once completed, it will be the largest optical and near-infrared telescope in the world, with a staggering 39-meter primary mirror. ELT is designed to achieve an unprecedented combination of light-gathering power and spatial resolution. It will be able to directly image stars in other galaxies, dissect their light into detailed spectra, and resolve stellar populations within dense star clusters like our 136 with astonishing precision. The ELT will allow astronomers to conduct close-up analyses of individual stars in our 136, separating their light from neighboring stars in this densely packed cluster. One of the key goals will be to determine if our 136A1 is truly a single star or a close binary or multiple star system masquerading as one ultra-bright object. This has been a topic of much debate among astrophysicists. High-resolution spectroscopy from the ELT could detect the subtle Doppler shifts caused by orbiting stellar companions, something no current telescope has been able to do with sufficient clarity for a star as remote and complicated as our 136A1. In addition, ELT will be equipped with adaptive optics systems that compensate for the distortion caused by Earth's atmosphere. This will give it Hubble-like sharpness from the ground, a massive improvement over previous generations of ground-based observatories. With this level of detail, the ELT will also be able to monitor stellar variability in our 136A1 and similar stars, tracking their changes in brightness, wind velocity, and temperature over time. Such observations will deepen our understanding of the instability mechanisms that plague massive stars and the events that might lead up to their eventual demise. And we're not stopping there. Other facilities like the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, are also in development, adding to this global network of ultra-powerful observatories. Together, these instruments will build an observational synergy that allows astronomers to cross-reference and confirm discoveries made with different methods and wavelengths, from optical to infrared and beyond. Even more exciting is the possibility that these observatories could detect stars even more massive than our 136A1, or at least confirm whether such stars can theoretically exist. For now, our 136A1 is the upper known limit, but that boundary may be a moving target. If JWST or ELT finds stars that are even slightly larger, or detects compelling evidence of massive stellar mergers in young clusters, our concept of the stellar mass ceiling will be forced to evolve. Furthermore, as scientists use JWST and ELT to study the life cycles of massive stars across different galaxies, they'll start to build a comparative database. By understanding how environment, metallicity, and cosmic time affect the formation and evolution of stars like our 136A1, we can better map the life cycle of matter in the universe, how it moves from gas to star to explosion and back to gas again, seeding the cosmos with the elements necessary for planets, and ultimately, life. One of the longer-term goals of these observatories will be to search for the precursors and aftermaths of massive stellar deaths. This includes identifying potential progenitors of hypernovae or gamma-ray bursts, and tracking their remnants to study the formation of black holes or neutron stars. Our 136A1 provides a kind of Rosetta Stone in this context, a living example of the kind of star that may one day become one of the most violent events in the universe. The data gathered from our 136A1 and its stellar siblings will not only test existing astrophysical models but could also uncover entirely new physical phenomena. For instance, questions about radiation pressure, mass loss through stellar winds, and magnetic field generation in extreme stars remain open. These stars operate on physical scales so extreme that they serve as natural laboratories for high-energy physics, allowing us to test ideas that are impossible to replicate on Earth. In the hands of scientists using JWST and ELT, our 136A1 becomes more than just an astronomical curiosity. It becomes a gateway, a key to unlock the secrets of stellar extremes, cosmic feedback, and the violent, beautiful mechanisms that govern the birth and death of stars. What we uncover in the coming decades will likely redefine our understanding not only of massive stars, but of the universe itself. In the vastness of space, where order seems to govern the dance of stars and galaxies, there are still things that defy our deepest knowledge, objects so extreme that they seem to stand at the very edges of what the cosmos should be able to produce. Our 136A1 is one of those objects. It is, by all accounts, a star that shouldn't exist. And yet it does. Blazing with more than 8 million times the luminosity of our Sun, weighing over 200 solar masses, and radiating at temperatures exceeding 50,000 Kelvin, our 136A1 is not just a giant, it's a cosmic anomaly. A paradox wrapped in hydrogen, helium, and light. The very existence of our 136A1 flies in the face of traditional stellar evolution theory. For decades, scientists believed there was an upper mass limit to how large a star could get, somewhere around 150 times the mass of our Sun. That wasn't a random number, either. It was the outcome of decades of simulations, equations, and observations. A balance between radiation pressure and gravity was thought to prevent any larger accumulation of stellar material. Gravity would collapse the core, but radiation, the immense energy produced through fusion, would push outward and blow off any excess mass before it could settle. That limit made sense. It helped explain the distribution of star sizes we saw across the sky. It fit nicely into our models of how stars are born, live, and die. And then our 136A1 was discovered, too big, too bright, and too powerful to ignore. This single object has thrown a wrench into the gears of astrophysics. Every attempt to make it fit into our models feels like stretching reality to accommodate a puzzle piece from another box. It's like finding a skyscraper on the moon, not impossible, but so improbable that it forces us to reconsider everything we thought we knew about the environment that produced it. But that's what makes our 136A1 so captivating. It's not just the biggest or brightest, it's the fact that it shouldn't be anything at all. And yet, here it is, standing as a defiant exception to our rules, challenging us to look harder, dig deeper, and rethink the universe. Because maybe it's not our 136A1 that's wrong. Maybe it's our understanding that's incomplete. Science thrives on anomalies. Every time we find something that doesn't fit, we gain an opportunity, a crack in the armor of our ignorance. Our 136A1 may well be one of the most important such anomalies of our time. It demands better models of star formation. It forces us to revisit the role of stellar feedback in dense clusters. It challenges the very notion of what stars are capable of becoming. Is it a single star? A merger of many? A rare byproduct of a particularly chaotic environment? Or is it something we haven't even thought of yet? This star is not just a test of physics, it's a test of imagination. The mere act of observing our 136A1 has already expanded our conception of the universe. And its legacy will likely continue to shape the frontier of astronomy for decades to come. As our instruments become more sensitive and our models more sophisticated, we will surely revisit this stellar titan again and again, chipping away at its mysteries, one photon at a time. And even after it's gone, after it explodes in some cataclysmic supernova, or hypernova, or collapses silently into a black hole, its story won't end. The light from its explosion will travel across the cosmos, reaching distant worlds and civilizations, whispering of a giant that once dared to exist. It is humbling to think that such a star, so far away and so distant in time, could hold such immense power, not only in its physical presence but in its ability to shape our understanding. Stars like our 136A1 remind us that the universe is still wild, still mysterious, and still far beyond the limits of our complete understanding. So the next time you look up at the night sky, remember, among those twinkling dots of light, there are monsters. Titans. Phenomena that stretch the very laws of nature. And somewhere, in a distant arm of the large Magellanic Cloud, a star that shouldn't exist continues to shine, if only for a brief cosmic moment, pushing back the dark and daring us to explain it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.